Look up at the night sky, at that familiar canvas of twinkling lights. We grow up learning the names of the planets, the order they orbit the sun, the basic story of our solar system. It feels settled, explained, almost ordinary. But what if that's just an illusion? What if the reality is that we are living in the midst of one of the greatest mystery novels ever written, and we've only just begun to read the first page? What if everything we think we know about our cosmic neighborhood is profoundly, spectacularly wrong? The truth is, our solar system is not a quiet, predictable place. It is a stage for phenomena so strange, so utterly baffling, that they defy our current understanding of physics and reality itself. We are surrounded by whispers of the impossible, clues to puzzles we haven't even fully learned how to solve. This isn't about distant galaxies or theoretical realms. This is about our own backyard, the planets and moons we call our neighbors, hiding secrets in plain sight. Today, we are setting out on a journey to explore these enigmas. We will venture from the scorching surface of Mercury to the frozen edges of the Kuiper Belt, uncovering 25 of the most head-scratching, mind-bending, unexplained phenomena in the solar system. We are talking about moons that shouldn't have atmospheres but do, planets with hexagon-shaped storms that rage for decades, magnetic fields that behave in ways that leave physicists utterly stumped, and signals from space that hint at forces we cannot yet name. Each one of these mysteries is a crack in the foundation of our knowledge, a glimpse into a universe far more complex and wondrous than we ever imagined. This is a voyage into the great unknown, and it begins right here where we least expect it. So, prepare to have everything you thought you knew about our little corner of the cosmos challenged. We are about to pull back the curtain on a solar system that is alive with questions, a place where the line between science and science fiction beautifully blurs. This is an invitation to rediscover your sense of wonder, to look up at the sky with fresh eyes, and to join us as we count down the 25 most compelling cosmic puzzles that are waiting right now for someone to find the key. The journey starts now, and we begin our countdown not in the cold, dark reaches of the outer solar system, but closer to home with our so-called sister planet, Venus. Shrouded in thick, toxic clouds of sulfuric acid, Venus has long been considered a hellish world with surface temperatures hot enough to melt lead. But high above that blistering surface at the planet's south pole, there exists a feature so bizarre it looks like something from a meteorological fantasy. This is the Venus vortex, a permanent, double-eyed hurricane that has been raging for decades, and it presents a puzzle that atmospheric scientists are still struggling to solve. The story of its discovery is a testament to how much we still have to learn about our nearest planetary neighbor. It wasn't until the European Space Agency's Venus Express orbiter arrived in 2006 that we got our first good look at the planet's polar regions. What the spacecraft saw astonished everyone. There, spinning over the South Pole, was a massive, violent storm with not one, but two distinct centers, a double vortex, coiling around each other in a complex and beautiful dance. From above, this structure resembles a giant, shifting figure eight or an immense pair of eyes staring out from the swirling clouds of Venus. This isn't a temporary weather event. It's a permanent fixture, a storm that has been locked in place for as long as we have been able to observe it. What makes this vortex so confounding for scientists isn't just its strange shape, but the environment in which it exists. Venus's atmosphere is a place of extremes. The entire envelope of gas whips around the planet in a phenomenon known as superrotation, completing a full circle around Venus in just 4 Earth days, while the planet itself takes 243 days to complete a single, sluggish rotation. This means the winds are screaming around the planet at hundreds of kilometers per hour, far faster than the surface rotates. In such a chaotic, high-speed system, how can a single, structured storm remain so stable and fixed at the pole? On Earth, hurricanes are fueled by warm ocean water and are steered by atmospheric currents, eventually losing power and dissipating over land or cooler seas. But on Venus, there is no ocean. The vortex seems to draw its energy and maintain its form from processes we don't fully understand, processes hidden deep within the planet's bizarre atmospheric circulation. The very presence of this double vortex challenges our most sophisticated climate models. When scientists try to simulate the conditions on Venus, their computers often produce a single vortex, similar to the hurricane-like eye we see at Earth's poles. Sometimes the models produce a vortex that splits apart and reforms, but the persistent, stable, double-lobed structure we observe is something they have a very hard time recreating. This tells us that there are fundamental forces at work in Venus's atmosphere, perhaps related to heat distribution, cloud chemistry, or interactions with the surface, that our models are currently missing. The Venus vortex is more than just a curious storm. It is a constant reminder that even the most familiar planets can harbor profound secrets, forcing us to question and refine our understanding of how weather works on a planetary scale. Leaving the swirling vortex of Venus behind, we journey next to the world that has captivated our imagination for generations, the red planet Mars. For centuries, we've looked at this rusty neighbor as a potential abode for life, a dry and dusty desert that may have once flowed with water. But one of the most tantalizing clues in this search hasn't been a fossil or a canal, but a whiff of gas. This brings us to our second great solar system mystery, the enigmatic case of Martian methane. On Earth, the vast majority of methane in our atmosphere is produced by living organisms. From the digestive processes of cattle to the decay of plants in wetlands, this simple gas, just one carbon atom bonded to 4 hydrogen atoms, is a prominent signature of biology. So, when our robotic scouts on Mars began detecting this very same gas sporadically appearing in the thin Martian air, the scientific community was electrified. Could this be the first faint signal that we are not alone? Or is it merely the product of non-living geological processes? This question lies at the heart of a detective story that has been unfolding for decades, full of conflicting evidence and passionate debate. The plot began to thicken in 2004, when the European Space Agency's Mars Express orbiter first reported traces of methane in the Martian atmosphere. Then, in 2013, NASA Curiosity rover, trundling across the floor of Gale crater, made an even more startling discovery. It didn't just detect methane in the general atmosphere. It recorded sudden, dramatic spikes where the methane concentration would soar to around 10 times the background level, only to vanish again just as quickly. These burps of gas were localized and transient, suggesting that something was actively producing or releasing the methane right then and there, and that the gas was being rapidly destroyed. This behavior is one of the most perplexing aspects of the whole mystery. The Martian atmosphere contains hydroxyl radicals that act like a cosmic cleaning agent, breaking down methane molecules within a few hundred years, a geological blink of an eye. For us to be detecting it now in these sudden surges means the source must be recent and ongoing. So, what is creating it? Scientists are essentially divided into 2 camps. The first and most exciting possibility is a biological one. Deep beneath the frozen Martian soil, in hidden aquifers protected from the harsh surface radiation, could there be microscopic methane-producing microbes? On Earth, such organisms, called methanogens, thrive in oxygen-poor environments like deep underground rocks or the guts of animals. They don't need oxygen, they produce methane as a byproduct of their metabolism. The idea that similar life could be eking out an existence in the subterranean darkness of Mars is a profoundly compelling hypothesis. The other, more conservative explanation points to geology. Methane can also be produced abiotically without any life involved through a process called serpentinization. This occurs when certain types of rock, like olivine, react with water in a chemical process that releases methane as a byproduct. We see this happen on Earth in places like hydrothermal vents. Mars has plenty of the right rocks and strong evidence of a watery past. It's entirely possible that pockets of water are still interacting with these minerals deep underground, occasionally venting the resulting methane gas to the surface through cracks and fissures. The debate is far from settled because every new piece of data seems to add another layer of intrigue. For instance, the Trace Gas Orbiter, a more recent and highly sensitive European-Russian mission designed specifically to sniff out atmospheric gases, has reported an unexpected finding. It has generally found the Martian atmosphere to be almost completely devoid of methane, contradicting the rover's localized measurements. This contradiction itself is a mystery. It could mean that the methane releases are extremely localized and brief, and the orbiter simply hasn't flown over the right spot at the right time. Or it could point to an unknown atmospheric process that is destroying the methane far more quickly than we thought possible. This scientific tug of war makes the Martian methane mystery one of the most dynamic and consequential puzzles in all of planetary science. It's a riddle where the stakes couldn't be higher, forcing us to ask one of humanity's oldest questions: are we truly alone? With every new day to point from our robotic emissaries on the red planet, we are inching closer to an answer, one elusive whiff of gas at a time. But the mysteries of our solar system are not confined to the atmospheres of other planets. Sometimes they come crashing down to our own world, leaving behind a scar of devastation and a puzzle that echoes for more than a century. This brings us to our third phenomenon, the Tunguska event, a cataclysm that remains the largest impact event in recorded human history, yet left no crater to tell its tale. Early on the morning of June 30th, 1908, in a remote and largely uninhabited part of Siberia, a man sitting on the front porch of a trading post was violently thrown from his chair. The sky, as he would later describe it, split in two, and a colossal pillar of fire appeared, followed by a series of thunderous blasts that shattered windows hundreds of kilometers away. The seismic shockwave was so powerful it registered on barometers as far away as England. What he had witnessed was the beginning of an event that would flatten over 2,000 square kilometers of pristine Siberian forest, an area nearly the size of a major metropolitan city. When the first scientific expedition finally reached the site almost 20 years later, led by the determined mineralogist Leonid Kulik, they were met with a scene of almost apocalyptic destruction. Millions of trees were snapped and laid out radially from a central point, all pointing away from the epicenter, like a forest of giant matchsticks tossed aside by an unfathomable hand. Yet, at the very center of this devastation, where Kulik fully expected to find a massive meteorite crater, there was nothing. The trees were still standing, scorched and stripped of their branches, but upright. It was as if the destructive force had simply vanished in mid-air. This complete absence of an impact crater is the core of the Tunguska enigma, and the reason it continues to captivate and baffle scientists. The leading and most widely accepted theory is that a relatively small asteroid or a piece of a comet, roughly 50 to 60 meters across, entered Earth's atmosphere at a shallow angle and a tremendous speed of tens of thousands of kilometers per hour. The intense friction and pressure of slamming into the thicker layers of our atmosphere caused the object to heat up catastrophically, resulting in a massive explosion several kilometers above the ground. This type of event is known as an airburst. The energy released is estimated to have been equivalent to 10 to 15 million tons of TNT. That's about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The blast wave, radiating downward from the point of explosion, is what flattened the forest, while the heat flash scorched the trees directly below. Because the object disintegrated completely in the air, no substantial fragments and certainly no crater were left behind. It was a cosmic bullet that vaporized just before it could strike the Earth. But the lack of conclusive physical evidence has naturally given rise to a host of more exotic explanations. Over the decades, scientists have proposed a wild variety of alternative theories to explain the unique nature of the devastation. One of the most fascinating, though largely discredited today, was the idea of a mini black hole. In the 1970s, physicists suggested that a primordial black hole, no larger than an atom but with the mass of a large asteroid, could have passed straight through the Earth, entering in Siberia and exiting out the other side of the planet. This, they argued, would explain the lack of a crater and the specific patterns of the shock waves. However, such an object would have left a detectable signature as it exited the atmosphere somewhere in the North Atlantic, and no such event was ever recorded. Other theories have included the antimatter annihilation of a chunk of rock from an antimatter asteroid, or the catastrophic explosion of a massive pocket of natural gas that had seeped from the ground. While creative, these ideas generally fail to account for the observed evidence as neatly as the asteroid airburst hypothesis. So why does Tunguska still matter today, over 100 years later? Because it serves as a stark and sobering reminder of our planet's vulnerability. The Tunguska event literally happened in one of the few places on Earth where it could cause minimal human casualties. If an object of that size were to airburst over a densely populated urban center today, the results would be catastrophic, leveling an entire city and causing millions of deaths. It underscores the critical importance of planetary defense programs that are now actively scanning the skies for near-Earth objects. Yet, despite all our advances, the Tunguska event retains its essential mystery. We have a compelling theory, but we lack the smoking gun, the irrefutable fragment of the impactor that would finally close the case. This gap between a strong hypothesis and absolute proof is what keeps the door open for speculation and continued scientific inquiry, ensuring that this Siberian mystery continues to challenge our understanding of the threats and wonders that drift through our cosmic neighborhood. From the frozen silence of Siberia, we now direct our gaze outward toward the gas giants, where the very definition of a storm is rewritten on a scale that dwarfs our entire world. If the phenomena we've explored so far feel like local mysteries, the next two are titans of atmospheric chaos, showcasing the raw, untamed power of planetary weather systems. We are moving to Jupiter and Neptune to confront two colossal storms that stand in stark contrast to one another. One an ancient, enduring behemoth, and the other a ghost that appeared and vanished before our very eyes. Let's start with the King of Storms, the one feature of Jupiter that has been a constant in our telescopes for as long as we have pointed them skyward, the Great Red Spot. This is not merely a storm, it is a planetary institution. When early astronomers first documented its swirling, brick red presence over 350 years ago, they were looking at a tempest that was already likely centuries old. To put its sheer size into perspective, for most of recorded history, the Great Red Spot was so vast that you could fit 2 or even 3 Earths inside its turbulent boundaries. It is a hurricane-like system, but one that operates on a logic entirely its own, an anticyclonic storm, meaning it rotates in the opposite direction to the hurricanes we experience on Earth. It's a high-pressure vortex, a massive, swirling pancake of gas that sits wedged between two of Jupiter's powerful, opposing jet streams, perpetually churning in a confined space. The central mystery of the Great Red Spot has always been its breathtaking longevity. How can a storm possibly rage for centuries or even millennia without running out of energy? On Earth, hurricanes are born over warm ocean waters and die when they move over land or cooler seas, their fuel source cut off. Jupiter, however, is a planet without a solid surface. It is a deep, churning ball of hydrogen and helium, all the way down to a possible core of metallic hydrogen. The storm draws its energy not from solar heat or ocean evaporation, but from the planet's own immense internal furnace. Jupiter radiates more heat than it receives from the Sun, a remnant of its violent formation. This internal heat drives the planet's unbelievable atmospheric convection, creating the powerful jet streams that have, in effect, trapped and fed the Great Red Spot, making it a self-sustaining engine of chaos. Yet, even this ancient titan is not immune to change. In recent decades, our observations from spacecraft like Voyager and Juno have shown the spot is undergoing a transformation. It is shrinking, it's becoming more circular, and its iconic red color has been deepening and fading in cycles we don't fully understand. Some scientists even speculated could eventually dissipate entirely within our lifetimes, a thought that is both scientifically fascinating and strangely poignant. The exact chemistry that gives it that distinctive red hue is still debated, with theories ranging from complex sulfur and phosphorus compounds being upwelled from deeper within Jupiter's atmosphere, to the effects of solar ultraviolet radiation breaking down simple chemicals. The Great Red Spot is a living, breathing, and evolving puzzle, a storm that has witnessed the entirety of modern science and continues to challenge our understanding of fluid dynamics on a planetary scale. Now, let's travel to the solar system's outermost ice giant, Neptune, where we find a storm that presents the complete opposite mystery. While Jupiter's spot is a monument to permanence, Neptune's great dark spot is a lesson in evanescence. When Voyager 2 flew past Neptune in 1989, it revealed a world that, despite receiving only a fraction of the solar energy that Jupiter does, possessed the fiercest winds in the entire solar system, screaming at speeds over 2,000 kilometers per hour. And there, in its southern hemisphere, was a feature that looked hauntingly familiar. A great dark spot, an Earth-sized anticyclonic storm very much like a blue-hued cousin to Jupiter's famous vortex. Scientists were thrilled. Was this a permanent feature of Neptune as well? We only had to wait a few years for the answer. When the Hubble Space Telescope turned its powerful eye toward Neptune in the mid-1990s to take another look, the great dark spot was gone. It had simply vanished without a trace. This disappearance was a profound shock to planetary scientists and completely upended their models of atmospheric behavior. How could a storm system large enough to swallow our planet simply cease to exist in such a short period? The prevailing theory is that these great dark spots on Neptune are not rooted deep in the planet's atmosphere like Jupiter's spot seems to be. Instead, they are thought to be immense eruptions of darker material from the lower atmosphere that punch up into the upper, brighter cloud decks, creating a visible hole or vortex. They are likely much more shallow and transient features. Since the original spot vanished, Hubble and other telescopes have observed other dark spots appearing and disappearing on Neptune, confirming that this is a recurring but fleeting phenomenon. The atmosphere on Neptune is so dynamically active and its wind shears so extreme that these colossal storms are simply torn apart, dissipated, or perhaps sink back down into the depths from which they came, all within a few Earth years. This creates a stark and beautiful contrast between our two gas giants. Jupiter showcases a storm of almost geological timescales, a stable system in a turbulent environment. Neptune, on the other hand, demonstrates a weather system of breathtaking impermanence where Earth-sized tempests can be born, live, and die within a human childhood, reminding us that the forces shaping our solar system are as varied and unpredictable as the planets themselves. But our journey through the solar system's mysteries now takes us beyond the familiar planets and moons, beyond even the realm of physical objects, and into the silent, invisible ocean of radio waves that fills the void. Here we encounter a ghost in the cosmic machine, a signal that lasted for just 72 seconds but has echoed through the decades as one of the most compelling and unexplained events in the history of astronomy. This is the story of the WOW signal. The setting for this cosmic detective story was the late summer of 1977. At the Big Ear Radio Telescope in Delaware, Ohio, a dedicated volunteer named Jerry Amon was part of the Search for Extraterrestrial Intelligence, or SETI, project. His task was to sift through reams of computer printouts, long sheets of paper filled with columns of alphanumeric data representing the faint radio whispers picked up by the telescope from the depths of space. The system was designed to flag any signal that matched the profile of a potential artificial transmission, specifically a powerful, narrowband signal coming from a specific point in the sky, unlike the broad, natural static emitted by stars and galaxies. On August 15th, as Amon was reviewing data from a few days prior, his eye caught something that made him freeze. On the printout, next to a sequence of characters representing an intense burst of radio waves, he circled the alphanumeric code 6EQUJ5 and in red pen wrote a single powerful word in the margin: "Wow." That annotation, a spontaneous expression of stunned amazement, is what gave the signal its immortal name, and what exactly had so astonished him. The signal was a stunningly pure, narrowband radio blast at the frequency of 1,420 MHz, a frequency that happens to be in a protected band of the radio spectrum where earthly transmissions are forbidden. It was incredibly strong, peaking at a level 30 times higher than the background noise of space. Most importantly, it exhibited the exact signature that SETI scientists had predicted for an artificial interstellar beacon. Because the Big Ear telescope used two separate feed horns to scan the sky, the signal was expected to rise to a peak intensity as it passed under the first horn, drop down, and then rise again as it passed under the second horn about 72 seconds later. The WOW signal did exactly that. It appeared, reached its incredible peak, and then vanished, having passed completely through the telescope's field of view in just over a minute. It was, in every technical sense, the perfect candidate for a message from another civilization. In the years and decades that followed, astronomers mounted an exhaustive search to find the signal again. They pointed telescopes back to that same patch of sky in the constellation Sagittarius, scanning for a repeat performance for any hint of the source. They considered and systematically ruled out every conceivable natural or human-made explanation. It wasn't a passing satellite or aircraft, as those would have left a different moving signature. It wasn't a random burst from a known celestial object like a pulsar or quasar, which produce broad-spectrum noise, not a sharp, narrowband signal. It wasn't military testing, and it wasn't reflected radio interference from the Earth's own surface. Every time a new theory was proposed, from a comet's hydrogen cloud to a bizarre form of interstellar plasma scintillation, the specific details of the signal's frequency, duration, and intensity have ultimately debunked it. The source of the WOW signal remains stubbornly, profoundly silent. This single, unverified, and unrepeated event stands as a monument to both the promise and the profound challenge of SETI. It is a data point of one, a tantalizing clue that is impossible to verify and impossible to ignore. It represents the ultimate what if. What if, for just 72 seconds in 1977, we accidentally tuned into a cosmic broadcast? What if it was a lighthouse beam from a distant civilization, sweeping across our solar system and momentarily illuminating our tiny, listening telescope before continuing on its journey through the galaxy? The frustrating and beautiful truth is that we may never know. The WOW signal is a perfect cosmic mystery, a brief, brilliant flash of possibility that continues to haunt our imagination and drive our search for answers, a solitary whisper in the static that asks the most profound question of all: was anyone out there just for a moment trying to say hello? Yet, as we contemplate signals from the stars and storms on other worlds, we must also confront a mystery that hits much closer to home, a paradox written into the very history of our own planet. This enigma is known as the faint young sun paradox, and it challenges our fundamental understanding of Earth's climate and its relationship with our star. The problem is deceptively simple, yet its implications are profound. According to our most robust models of stellar evolution, the Sun, in its youth about 4 billion years ago, was significantly dimmer, roughly 30% less luminous than it is today. Stars like our Sun gradually brighten as they age, as the fusion process in their core changes over billions of years. If we take that fainter Sun and place our modern Earth under it, with its current atmosphere and ice cover, the entire planet should have been a global, frozen snowball. The average global temperature would have been well below the freezing point of water, but here's the stunning contradiction. The geological record tells a completely different story. The ancient rocks of Earth, some of the oldest we can find, provide clear and undeniable evidence that our planet was awash with liquid water during this very period. We see sedimentary deposits that formed in rivers and oceans, and we find pillow lava structures that only form when lava erupts underwater. Most compellingly, we find fossils of single-celled life that date back over 3.5 billion years, organisms that lived in a liquid water environment. So, the evidence is unequivocal. Earth was warm and wet when, by all rights, it should have been cold and icy. This is the paradox, a planet that defied the physics of its own time, creating a cozy, habitable cradle for life under a dim, young star. How did Earth solve this climatic puzzle? Scientists have been grappling with this question for decades, and the leading hypothesis points to a powerful, primordial greenhouse effect. The thinking is that Earth's early atmosphere must have been far richer in heat-trapping greenhouse gases than it is today, creating an insulating blanket thick enough to compensate for the lack of solar warmth. The prime suspect for a long time was carbon dioxide. A much denser CO2 atmosphere, perhaps tens or even hundreds of times thicker than today's, could theoretically have provided the necessary warming. However, when geologists look for evidence of such high carbon dioxide levels in ancient soils and minerals, the data often doesn't support a CO2 level high enough to do the job alone. This has forced researchers to consider other, even more potent greenhouse gases. One fascinating candidate is methane. In an atmosphere with little to no oxygen, methane can build up to significant levels and is a tremendously effective greenhouse gas. It's possible that early microbial life, specifically methanogens, were already thriving and releasing vast quantities of methane, creating a kind of biological thermostat that kept the planet warm. Another compelling theory involves ammonia. While ammonia is fragile and easily broken down by sunlight, some researchers suggest that organic hazes or other protective chemicals in the atmosphere could have shielded it, allowing it to persist and contribute to a strong greenhouse effect. There are also non-atmospheric solutions. Perhaps the young Earth was simply darker, with less reflective landmasses and no bright, white ice caps to bounce sunlight back into space. A darker planet absorbs more solar energy, which could have provided a critical few degrees of extra warmth. It's also possible that the planet's spin or axial tilt was different, changing its climate dynamics in ways that prevented a global freeze. The truth is, no single solution has yet emerged as the definitive answer, and it's likely that the resolution involves a combination of these factors, a unique atmospheric cocktail and planetary conditions that worked in concert to keep the water flowing. This paradox is far from a mere historical curiosity. It is a vital key to understanding the delicate balance that makes a planet habitable. As we discover more and more exoplanets orbiting other stars, many of which are faint red dwarfs, the lessons from the faint young sun paradox become incredibly relevant. It tells us that a planet's habitability isn't just a simple function of its distance from its star. It's a complex interplay of atmospheric chemistry, geological activity, and even biology itself. Our own world, it seems, found a way to thrive against the odds, and uncovering its secret is one of the most important quests in all of planetary science. Leaving behind the chaotic storms of Jupiter and Neptune, we arrive at a world that seems to embody cosmic order, only to present us with a geometric riddle that defies all expectations. This brings us to the ringed giant, Saturn, and a feature so geometrically perfect it looks as though it was drawn by the hand of a celestial mathematician. High above Saturn's north pole, shrouded in the planet's long winter darkness for years at a time, there spins a colossal hexagon. This is not a temporary cloud formation or a trick of perspective. It is a permanent, six-sided jet stream, a hurricane over 30,000 kilometers wide, so vast that the entire Earth could fit comfortably inside its boundaries, and it has been steadily rotating there for decades, perhaps even centuries. The discovery of this phenomenon is a story of technological patience. For a long time, Saturn's north pole was hidden from our view, locked in the deep cold of its long seasonal night. Our first fleeting glimpses came from the Voyager flybys in the early 1980s, but the images were distant and lacked detail. It wasn't until NASA Cassini spacecraft arrived in the mid-2000s and began its long orbital tour that we finally got a clear, sustained look at the pole. What Cassini saw, particularly in its infrared and visible light mosaics, was nothing short of astonishing. There, encompassing the entire North Polar region, was a honeycomb cell of clouds, a near-perfect hexagon with sharply defined, almost straight walls. Each of the six sides is longer than the diameter of our own planet, and the entire structure rotates with a period of about 10 hours and 39 minutes, seemingly locked in sync with the planet's deep radio emissions. This isn't a static feature, it's a raging river of air, a jet stream racing along its hexagonal path, with winds screaming at speeds over 320 kilometers per hour. What makes Saturn's hexagon so uniquely baffling is the very nature of its geometry. In our experience, both on Earth and throughout the rest of the solar system, natural fluid dynamics in a rotating system tends to produce circular or spiral patterns. Think of hurricanes or Jupiter's great red spot, or even the vortex at Venus's pole. All are fundamentally circular or ovular. They are manifestations of what physicists call the Coriolis effect, the force that causes fluids and gases on a spinning sphere to curl. A stable, persistent hexagon is completely anomalous. It's as if you stirred a cup of tea and watched a perfect square form in the center of the vortex. It simply shouldn't happen according to our basic understanding. This suggests that some very specific and currently unknown set of conditions exists in Saturn's upper atmosphere that forces this turbulent, chaotic system into such an orderly and angular shape. Scientists have not been idle in the face of this puzzle. They have taken the challenge into the laboratory and onto their supercomputers in an attempt to recreate this six-sided wonder. The most compelling models suggest that the hexagon is a type of standing wave pattern, a stable Rossby wave that is pinned to Saturn's north pole. Imagine a wave frozen in place, but with the atmosphere streaming rapidly along its path. In laboratory experiments, researchers have placed a circular tank of fluid on a rotating table, representing Saturn's polar atmosphere. When they spin the fluid at different speeds, they can sometimes generate polygonal shapes, including hexagons and octagons at the center of the vortex. This happens when there is a steep latitudinal gradient in the speed of the wind, a sharp difference between a fast-moving jet stream and the slower-moving atmosphere surrounding it. On a supercomputer, similar conditions can be simulated in a virtual Saturn, and under the right parameters, a hexagonal flow pattern can indeed emerge and remain stable. These models are a triumph of modern geophysical fluid dynamics, but they are not yet a perfect solution. While they can produce the shape, they often struggle to replicate the hexagon's incredible longevity and razor-sharp boundaries over vast timescales. There seem to be missing ingredients in our understanding of the depth of Saturn's atmosphere, its internal heat flow, and the specific interactions between its cloud layers that are required to fully explain why this hexagon is so robust and unique in our solar system. The enduring presence of this geometric giant serves as a profound reminder of the complex and often alien physics that govern gas giant planets. It stands in stark contrast to every other atmospheric feature we have catalogued, a beacon of mathematical precision in a realm of untamed turbulence. While we have plausible theories for its existence, the Saturn hexagon remains at its heart, a majestic and enduring enigma, a planetary-scale work of art whose creator is the hidden, intricate machinery of Saturn's atmosphere itself. As we move beyond the orbit of Neptune, we enter a realm of darkness and ice, a vast donut-shaped region of frozen leftovers from the solar system's birth known as the Kuiper Belt. For decades, astronomers envisioned this distant zone as a gradually thinning cloud of icy worlds, with the number of objects slowly decreasing the farther out you go, eventually fading into the emptiness of interstellar space. But when our telescopes finally became powerful enough to map this frontier in detail, they revealed something completely unexpected. Instead of a gentle decline, we found a cliff. This is the Kuiper Belt Cliff, a sudden and dramatic drop in the number of objects at a distance of about 50 astronomical units from the Sun, 1 astronomical unit being the distance from the Earth to the Sun. It's as if you are walking along a beach where the sand gradually gets thinner, and then you abruptly reach a sharp edge with nothing but empty ocean beyond. This isn't just a curious statistical oddity. It's a boundary that challenges the very story we tell about how our solar system formed and what lies in its outermost reaches. The standard model of solar system formation, known as the NICE model, paints a picture of a relatively calm and structured process. It suggests that the planets coalesced from a swirling protoplanetary disk of gas and dust, and the Kuiper Belt is the remnant of that primordial material, shepherded into its current ring by the gravitational influence of Neptune. In this model, the density of objects in the Kuiper Belt should indeed taper off, but it should do so smoothly and predictably over a great distance. The existence of this sharp cliff, however, is like a glaring error in the calculation, a feature that the model does not account for and cannot easily explain. It implies that something dramatic happened out there, an event that either prevented objects from forming beyond that point or, more intriguingly, that swept the region clean of most of its inhabitants after they had already formed. This single observation forces astronomers to consider that the early solar system was a much more dynamic and violent place than we once believed, and it has given rise to 2 of the most fascinating and radical theories in modern planetary science. The first and most widely discussed theory is the existence of a massive, yet undiscovered planet lurking in the extreme outer darkness. This hypothetical world, often referred to as Planet 9, is not the tiny Pluto-like object some might imagine. Proposed to be a super-Earth or a mini-Neptune with a mass up to 10 times that of our own planet, its immense gravitational pull could be the sculptor of this cosmic cliff. The theory suggests that Planet 9's distant, elliptical orbit would act like a gravitational broom. As it swings through the outermost solar system on its long, multi-thousand-year journey around the Sun, its gravity would violently perturb the orbits of any smaller icy bodies in that region. Over billions of years, it would have flung the vast majority of them inward toward the Sun or entirely out of the solar system, leaving behind the stark, empty zone we observe today. The Kuiper Belt Cliff, in this scenario, is the edge of Planet 9's clearing influence, a lasting scar of its gravitational dominion. While the direct observational evidence for Planet 9 remains elusive, its hypothetical presence elegantly explains several other orbital anomalies observed in distant Kuiper Belt objects, which all seem to cluster in a way that suggests an unseen shepherd. The search for this phantom planet is one of the great astronomical quests of our time, a high-stakes game of celestial hide and seek where the Kuiper Belt Cliff serves as one of the most compelling pieces of circumstantial evidence. The second major theory offers an even more cataclysmic origin story for the cliff, one that involves a stellar intruder. Imagine the early solar system, still in its infancy, with the Kuiper belt a densely populated ring of icy planetesimals. Then another star, perhaps a sibling from the same birth cluster as our Sun, makes a close pass by our system. This is not as far-fetched as it sounds. Stellar nurseries are crowded places, and such flybys are thought to be relatively common in a young star's life. The gravitational tides from this passing star would have been immense, acting like a cosmic spoiler that ripped a vast number of objects from the outer solar system, dragging them away into interstellar space as the star receded. This event would have truncated the disk, creating a sharp, defined outer edge, the cliff we see today. This theory has gained traction with the discovery of a number of rogue interstellar objects, like Oumuamua, which suggest that there is a vast population of free-floating planetary building blocks between the stars, possibly ejected during such chaotic early encounters. While a stellar flyby is a one-time, dramatic event, it provides a neat solution without requiring a hidden, massive planet. However, it also raises new questions, such as why the inner solar system seems to have remained relatively unscathed by such a violent gravitational encounter. The debate between these two theories, a hidden planet versus a stellar flyby, is far from settled, and some scientists even suggest a combination of both factors could be at play. What makes the Kuiper Belt Cliff so compelling is that it is a cold, hard, observational fact that our best models cannot yet fully digest. It is a boundary written in ice and rock, a silent testament to a forgotten chapter of our solar system's history. Whether the culprit is a distant, unseen giant or the ghost of a passing sun, this mysterious edge forces us to acknowledge that our cosmic neighborhood may be far larger and more complex than our maps currently show, with its final borders still waiting to be drawn. But this journey through the vast and mysterious now brings us closer to home, to our most constant and familiar companion in the night sky, the moon. We've all grown up with the man in the moon, that same collection of dark Maria and bright highlands that has looked down upon every human who ever lived. We only ever see one face of our celestial neighbor, a fact so commonplace we rarely stop to consider just how strange it is. This phenomenon, known as tidal locking, is our 10th great solar system mystery, and while the basic physics behind it is understood, the specific story of our moon's locking presents a timeline so perfectly strange it feels almost arranged. The mechanism of tidal locking is an elegant dance of gravity and friction. The Earth's gravitational pull is stronger on the side of the moon that is closer to us and weaker on the far side. This difference, known as a tidal force, doesn't just cause the ocean tides on Earth. It also subtly stretches the moon itself, creating a slight bulge. Billions of years ago, when the moon was still molten and rotating more quickly, this gravitational tug would pull on that bulge, acting like a constant brake on the moon's spin. The internal friction within the moon's rock, as it was flexed by this pull, slowly sapped its rotational energy. Over eons, this process continued until the moon's rotation period slowed to exactly match its orbital period around the Earth. The result is what we see today, one perpetual face forever turned toward us, while the mysterious far side remains hidden from Earthbound view. This isn't a unique situation. Many moons in our solar system are tidally locked to their parent planets, from the large Galilean moons of Jupiter to Pluto's large moon, Charon, which is so large it's actually mutually locked with Pluto, creating a cosmic pair forever staring into each other. The true enigma of our moon's locking, however, lies not in the how, but in the when and the why. The prevailing theory of the moon's origin, the giant impact hypothesis, paints a violent picture. Early in the solar system's history, a Mars-sized body named Theia is thought to have slammed into the proto-Earth. The cataclysmic debris from this collision eventually coalesced to form the moon. Initially, this newborn moon was much closer to Earth and would have been spinning rapidly from the energy of the impact. Based on our models, the process of tidal locking should have taken around 100 million years to complete. Here's where the mystery deepens. The geological evidence suggests that the Moon became locked very early in its history, but not so early that the far side is fundamentally identical to the near side. In fact, the two hemispheres are shockingly different. The side we see is dominated by the dark, smooth plains of volcanic maria formed by ancient lava flows. The far side, however, is a rugged, crater-pocked landscape, almost entirely lacking these vast dark plains. This stark dichotomy suggests that the Moon was still hot and partially molten when it became locked. The Earth's gravity at that closer distance would have been immense, perhaps thick enough to make it harder for lava to erupt through the crust on the far side, or even influencing the distribution of the heat-producing elements that fueled the volcanic activity. The precise timing of the locking appears to have frozen in place a specific moment in the Moon's thermal evolution, creating a permanent geological asymmetry that we are only now, with modern orbiters, able to study in detail. This leads to an even more profound question. Is our situation common, or is it a rare cosmic quirk? The fact that we live on a planet with a large, tidally locked moon that presents a single face has had undeniable consequences for the development of science and culture. It gave us a constant, predictable celestial clock and calendar. It inspired myths, poetry, and the very first forays into astronomy. But if the Moon rotated just a little bit, showing us its other face, would our history have been different? From a purely statistical standpoint, tidal locking is a natural and common outcome for moons orbiting close to their planets. Yet, the specific conditions that led to our moon's formation, a giant impact creating a large satellite at just the right distance, might be far less common. As we look out at other star systems, we are beginning to find exoplanets that may themselves be tidally locked to their stars, presenting one scorching day side and one frigid night side. Our own moon, therefore, serves as a local laboratory for understanding a process that may be a fundamental feature of planetary systems across the galaxy. Its silent, one-faced vigil is a constant reminder that even the most familiar sights can hide a deep and dynamic history, a history written in gravity, time, and the lingering heat of a violent birth. From the silent, locked face of our moon, we now travel deeper into the solar system, to the asteroid belt that lies between the orbits of Mars and Jupiter. For centuries, this region was imagined as a chaotic jumble of rocks, the leftover rubble of a planet that failed to form. But when our spacecraft arrived for a closer look, they discovered that the largest object in this belt, the dwarf planet Ceres, was hiding a secret so brilliant it gleamed like a cosmic beacon. This brings us to our 11th mystery, the dazzling bright spots of Ceres, which transformed a small, icy world from a mere curiosity into one of the most geologically intriguing places in our solar system. The first hints of this enigma came as a Dawn spacecraft approached Ceres in early 2015. As the distant, pixelated world sharpened into focus, mission scientists were stunned to see a series of intensely bright patches scattered across its dark, cratered surface. The most prominent of these, a cluster of spots nestled inside the 57-mile-wide Ocata crater, shone with an albedo, a reflectivity, that was radically higher than the surrounding terrain. They were so brilliant that they initially saturated the cameras on the Dawn probe. What could possibly be so reflective on this small, cold world so far from the sun? Speculation ran wild. Some wondered if it was exposed water ice gleaming in the sunlight. Others, more fancifully, joked about alien cities. The truth, as revealed by Dawn's detailed orbital study, turned out to be stranger than anyone had anticipated and pointed to a world that was far from geologically dead. Dawn's suite of scientific instruments soon identified the primary composition of these bright spots as sodium carbonate, a kind of salt, essentially. This is the same material we find in vast deposits on Earth, like the famous white deserts of the American Southwest. Finding it in such concentrated, brilliant patches on Ceres was a complete shock. Sodium carbonate on Earth is often associated with places where water has evaporated, leaving the salts behind. Its presence on Ceres strongly suggested that, at some point in the relatively recent past, briny, salt-rich water had welled up from deep below the surface and reached the vacuum of space. There, the water would have instantly frozen or sublimated directly into vapor, leaving behind a spectacular, salt-encrusted deposit that reflects sunlight with incredible efficiency. The central, most dominant spot in Arcata, named Cerealia Facula, isn't just a simple patch. It's a complex dome, a mound of this bright material that appears to have been pushed up from below like a miniature salt volcano. This discovery immediately pointed toward a revolutionary idea. Ceres possesses a vast subsurface reservoir of briny water, a hidden ocean in the most unlikely of places. This isn't a global ocean like the one on Europa, but rather a deep layer of saturated rock, a so-called cryomagma chamber. The leading theory for the formation of the Arcata spots involves a powerful impact that created the crater itself millions of years ago. That colossal collision fractured the crust deep beneath the surface, creating a pathway for the brine reservoir below to be mobilized. The release of pressure, combined with residual heat from the impact, would have forced this salty slurry upward. It seeped through the fractures, eventually reaching the crater floor where it erupted or oozed out in a process known as cryovolcanism, but with icy water and salts instead of molten rock. The dome at the center of Cerealia Facula suggests this wasn't a one-time event. It likely involved multiple stages of upwelling, building the deposit layer by layer over time. Perhaps the most astounding part of this mystery is the evidence pointing toward recent, and possibly even ongoing, activity. The crater floor of Arcata is remarkably smooth and young-looking, with far fewer smaller impact craters scarring its surface than the surrounding ancient terrain. This indicates that some process resurfaced the area, erasing the evidence of older impacts. Furthermore, Dawn detected a tenuous, transient haze that occasionally appears inside Arcata crater, hanging above the bright spots. The most plausible explanation for this haze is that even now, deep below the surface, the reservoir remains active. Minute amounts of water vapor could still be escaping, lofting tiny ice and salt particles into a faint, localized atmosphere that condenses when illuminated by the sun. This paints a picture of Ceres as a dynamic, evolving world, not a frozen fossil. It's a place where internal heat and a vast, salty aquifer interact, occasionally bursting forth to paint the landscape with brilliant, white signatures of its hidden vitality. The bright spots of Ceres are therefore more than just a beautiful anomaly. They are a clear signal that even small, seemingly inert worlds can harbor complex geologic and perhaps even prebiotic processes, challenging our definitions of where to look for the ingredients of life. However, our journey doesn't end with the asteroid belt or even with the Kuiper belt. To find the true outermost boundary of our solar system, we must venture into a realm of pure theory, a place so distant and dark it has never been seen, only inferred. This is the Oort cloud, a hypothetical spherical shell of icy planetesimals that is thought to envelop our entire solar system like a vast gossamer cage. Its existence is one of the great deductions of modern astronomy, a necessary ghost whose presence is felt only through the occasional, spectacular visitors it sends careening into our inner cosmic neighborhood. The primary evidence for this distant cloud comes from the behavior of long-period comets. These are the comets that take thousands or even millions of years to complete a single, lopsided orbit around the Sun. They appear from seemingly random directions in the sky, not from the flat plane of the solar system where the planets and Kuiper belt reside. This isotropic distribution arriving from all points is the crucial clue. It tells us that the source of these comets must be a spherical shell, a reservoir that completely surrounds us. The Oort cloud is the only structure that fits this description. Astronomers hypothesize it is a colossal remnant of the solar system's original protoplanetary disk. a swarm of trillions of icy objects flung outward by the gravitational slingshot of the giant planets in our system's violent youth. These objects now populate a region of space that begins roughly 2,000 astronomical units from the Sun and may extend outward to a mind-numbing 100,000 astronomical units or more. To put that almost incomprehensible distance into perspective, the inner edge of the Oort cloud is about 1,000 times farther from the Sun than the Kuiper Belt Cliff. If the Voyager 1 probe, the most distant human-made object, were headed in that direction, it would take it nearly 30,000 years just to reach the Oort cloud's inner fringe. The profound challenge, and thus the central mystery of the Oort cloud, is that we cannot see it. It is simply too far away, its objects too small and too dim, reflecting virtually no sunlight back to our most powerful telescopes. We are like someone in the middle of a vast, dark ocean, trying to map the distant horizon by observing the rare, flickering light of a single passing ship. Those ships are the long-period comets themselves. When a chance gravitational nudge, perhaps from the subtle pull of a passing star or the tidal force of the Milky Way galaxy itself, dislodges one of these icy primordial bodies from its stable orbit in the Oort cloud, it begins a fall of tens of thousands of years inward toward the Sun. As it approaches the inner solar system, the Sun's heat vaporizes its ices, creating the glorious comas and tails that make these objects so spectacular in our night sky. Each long-period comet is therefore a messenger, a sample from the solar system's deepest freezer, carrying with it the pristine, unaltered chemistry of our system's birth over 4.5 billion years ago. This leads to the final and perhaps most profound mystery the Oort cloud represents. It is a fragile historical record, easily disturbed and reshaped by the galaxy around us. Because the objects in the Oort cloud are so loosely bound to the Sun by gravity, their orbits are incredibly sensitive to external influences. The gentle, cumulative gravity of the entire Milky Way galaxy can exert a tide that slowly stirs this distant reservoir. More dramatically, the occasional close pass of another star can act like a cue ball striking a cluster of balls, scattering countless comets inward toward the Sun or ejecting them into interstellar space forever. This means the Oort cloud we observe today is not the pristine cloud that formed. It has been sculpted and eroded over billions of years by these galactic interactions. By studying the orbits of the long-period comets that visit us, we are indirectly studying the history of our Sun's journey through the galaxy. We are reading a chronicle of which stars passed nearby and when. The Oort cloud is more than just a collection of icy rubble. It is a dynamic, living archive of our solar system's place in the cosmos, a vast and silent witness to the gravitational dances that have shaped our celestial neighborhood since the dawn of time. Its very existence, though still just beyond our sight, confirms that the influence of our Sun extends nearly halfway to the next star, and that our true home in the universe is far grander and more expansive than we could ever have imagined. And as we contemplate the vast, unseen boundaries of our solar system, it's worth remembering that sometimes the most puzzling clues aren't found in distant clouds or on alien surfaces, but in the precise trajectories of our own robotic explorers. This brings us to a mystery that was measured not in grand cataclysms or brilliant flashes, but in a whisper of speed lost over billions of miles, the enigma known as the Pioneer Anomaly. For decades, the twin spacecraft Pioneer 10 and Pioneer 11 were celebrated heroes of early space exploration. After completing their primary missions to Jupiter and Saturn, they continued on their incredible journeys, becoming the first human-made objects destined to leave our solar system entirely. But as they sped toward the stars, navigators at NASA, a jet propulsion laboratory, began to notice something peculiar in their tracking data. Both spacecraft were experiencing a tiny, unexpected, and constant deceleration. It was an almost imperceptible drag, a force pulling them back toward the Sun, equivalent to just 10 billion times weaker than the gravity we feel on Earth's surface. To put that in perspective, it was like having an extra gentle press on the brakes that slowed the pioneers by about 3,000 miles over the course of a single decade. For objects traveling at tens of thousands of miles per hour, this was a minuscule effect, but in the hyper-precise world of orbital mechanics, it was a glaring discrepancy that could not be ignored. This tiny anomaly became a massive headache for physicists. For over 30 years, it defied all conventional explanation. Was it some unknown form of dark matter exerting a drag? Could it be a flaw in our understanding of gravity itself? A hint that Einstein's theory of general relativity needed a tweak at the vast scales of the solar system. Some even proposed more exotic ideas, like the influence of extra dimensions. The Pioneer anomaly represented a classic scientific puzzle, a clear, consistent signal that our best models of the universe could not account for. It was a ghost in the machine of deep space navigation, a mystery that lingered in the background of cosmology, suggesting that perhaps our grasp of fundamental physics was not as complete as we had believed. The solution, when it finally came, was not a rewrite of the laws of physics, but a masterpiece of forensic engineering and a profound lesson in humility. The key was recognizing that the spacecraft themselves were the source of the mystery. The Pioneers were powered by radioactive thermoelectric generators, which produced heat that was then converted into electricity. This process also meant the spacecraft were essentially floating power sources radiating waste heat. A team of researchers, after years of painstaking work, managed to recover and analyze old telemetry data and even original design documents. They created a complex thermal model of the spacecraft, accounting for every watt of heat emanating from their electronics and from the plutonium power source. They realized that this heat didn't just radiate away equally in all directions. A significant portion was being emitted from the back of the spacecraft's main dish antenna. According to the simple physics of thermal radiation, every photon carrying away that heat also carries a tiny amount of momentum. When the photon is emitted in one direction, it gives the spacecraft a minuscule push in the opposite direction, much like a very, very gentle rocket engine. Because the main antenna was pointed back toward Earth and thus toward the Sun, this thermal radiation was acting as a constant, very faint break, producing exactly the amount of anomalous deceleration that had baffled scientists for so long. The resolution of the Pioneer anomaly stands as a powerful reminder of the importance of mundane, systematic effects. It highlights the incredible precision required for interplanetary travel, where something as seemingly insignificant as the warmth of a spacecraft's components can, over years and across billions of miles, create a measurable drift in its course. It also serves as a cautionary tale for scientists. Sometimes the most tantalizing evidence for new physics can turn out to be a previously overlooked detail of engineering. Yet the decades-long investigation was far from a waste of time. The intense scrutiny forced upon the Pioneer's trajectory has led to vastly improved navigational models for all our deep space missions, ensuring that the Voyager probe's new horizons and future interstellar travelers have a more accurate map of the void. The anomaly may have been solved, but its legacy is one of refined precision and a deeper appreciation for the hidden complexities that accompany humanity's first steps into the cosmic ocean. But to truly understand the violent history of our solar system, we have to journey back to its very beginnings, to a cataclysmic era that may have been the crucible in which life itself was forged. This brings us to one of the most dramatic episodes in our planetary story, the Late Heavy Bombardment. Evidence gathered from the Moon, Mercury, and Mars points to a period of unimaginable violence around 4 billion years ago, a time when the inner solar system was subjected to a relentless, planet-shattering rain of asteroids and comets. The surfaces of these worlds bear the scars of this ancient onslaught in the form of immense, overlapping impact basins, a testament to a time of chaos that fundamentally reshaped the terrestrial planets and possibly even delivered the very ingredients for life to a once sterile Earth. The primary evidence for this cosmic shooting gallery comes from the most accessible archive we have, our own moon. The lunar highlands are ancient, heavily cratered terrain, but the large, dark basins known as Maria tell a more specific story. By analyzing the rocks brought back by the Apollo missions, scientists were able to radioactively date the lava that filled these basins. The stunning result was that many of the largest impacts, which created basins like Imbrium and Orientale, seem to have occurred in a relatively narrow window of time between about 4.1 and 3.8 billion years ago. This wasn't a steady drizzle of impacts from the solar system's formation. It was a sudden, intense storm that peaked long after the planets themselves had coalesced. The Earth, being a larger target with more powerful gravity, would have received an even more devastating pummeling during this period. While our planet's active geology has erased the direct cratered evidence, the lunar record serves as a stark proxy, telling us that our own world was once an inferno of impacts, with consequences that may have ranged from vaporizing any early oceans to, paradoxically, creating the conditions for life to emerge. What could have caused such a delayed cataclysm? The leading explanation is a grand and dynamic story of planetary migration, elegantly captured in what scientists call the Nice model, named for the city in France where it was developed. This model proposes that the giant planets Jupiter, Saturn, Uranus, and Neptune did not form in their current orbits. Initially, they were in a much more compact, closely packed configuration, nestled within a vast disk of leftover icy planetesimals beyond Neptune. Through subtle gravitational interactions, the planets began to slowly migrate. The pivotal moment came when Jupiter and Saturn fell into a specific orbital resonance, a gravitational lockstep where Saturn completed exactly 2 orbits for every one of Jupiter's. This resonance sent a powerful gravitational shockwave through the entire solar system, violently destabilizing the orbits of Uranus and Neptune. These ice giants were flung outward, plowing through the pristine disk of icy bodies like cosmic bulldozers. This event scattered the disk, flinging a vast swarm of these objects inward toward the Sun. For millions of years, this incoming hail of comets and asteroids bombarded the inner solar system, battering the young worlds and creating the scarred landscapes we see today on the Moon. The Nice model provides an elegant and mathematically sound trigger for the late heavy bombardment, turning a mysterious period of violence into a predicted consequence of our solar system's restless evolution. However, this grand narrative is not without its controversies and competing ideas. The timing of the late heavy bombardment is a particular point of debate. Some scientists argue that it wasn't a distinct, late-breaking cataclysm, but rather the tail end of a steadily declining reign of impacts that began with the solar system's formation. They point to potential biases in the lunar samples, suggesting that the Apollo missions may have predominantly collected material from a single, large impact basin, making it appear as if many impacts happened at once. Other models propose different triggers, such as the gravitational disruption from a since-ejected fifth giant planet, or even the tidal pull of a passing star in the Sun's birth cluster stirring up the primordial debris disk. Each theory has its strengths and weaknesses, and the search for more precise evidence continues, with future lunar missions aimed at sampling a wider variety of impact craters to build a more complete timeline. Regardless of the exact trigger, the implications of this bombardment are profound, especially for our own planet. This period of extreme violence may have been a double-edged sword for the emergence of life. On one hand, the energy from these colossal impacts would have been enough to repeatedly sterilize the Earth's surface, vaporizing any early oceans and incinerating any fragile prebiotic chemistry. It was an era of global infernos and shattered crust, yet on the other hand, these same impacts may have been essential delivery vehicles. Comets and water-rich asteroids are thought to be the primary source of Earth's water and organic molecules. The late heavy bombardment could have been the final, dramatic delivery of the oceans and the carbon-based building blocks that would eventually assemble into the first living organisms. It represents a cosmic paradox of destruction and creation, a tumultuous baptism that both threatened to snuff out the spark of life and yet may have provided the very fuel for it. This ancient cataclysm, written in the craters of the Moon, is therefore not just a historical curiosity. It is a fundamental chapter in our own origin story, a reminder that our existence may be the product of one of the most violent epochs in the history of our solar system. Now, let's shift our focus from these violent historical events to a fundamental and enduring property of the planets themselves, their spin. If you were to line up all the planets in the solar system and watch them rotate, you'd notice something immediately striking. The inner rocky worlds Mercury, Venus, Earth, and Mars all turn at a relatively leisurely pace, with days lasting anywhere from 24 hours to months. But when you get to the gas giants, everything changes. Jupiter, the solar system's behemoth, completes a full rotation in just under 10 hours. Saturn is even faster, spinning so rapidly that its day is only about 10.5 hours long. These are colossal worlds with diameters more than 10 times that of Earth, yet they whirl around like cosmic tops. This dramatic difference in rotation rates isn't a coincidence. It's a direct consequence of how these planets were born, and it leads us to one of the most fundamental principles in all of physics. The explanation begins with the conservation of angular momentum. To understand this, imagine a figure skater pulling in their arms during a spin. As they draw their mass closer to their axis of rotation, they spin faster and faster. They aren't adding new energy, they're simply redistributing their existing mass, and the total amount of spin, the angular momentum, must remain constant. This same principle, scaled up to a cosmic level, is the key to the gas giants' dizzying speeds. Our entire solar system formed from a massive, slowly rotating cloud of gas and dust called the protoplanetary disk. This primordial cloud had a tiny amount of overall spin inherited from the turbulent motions of the interstellar medium. As gravity caused the cloud to collapse inward, it had to spin faster, just like our figure skater. But the cloud wasn't a single, solid object. It was a vast disk where material gradually clumped together to form planets. The rocky planets in the inner solar system formed through the relatively slow process of accretion, where small dust grains and planetesimals collided and stuck together, building up a world piece by piece. This process involved a lot of collisions that could actually break the planet's spin, and they were also competing for material within a smaller, denser region of the disk closer to the Sun's immense gravity. The gas giants, however, had a completely different origin story that allowed them to gather and conserve an immense amount of this primordial spin. Beyond the frost line, where it was cold enough for volatile ices to exist, there was vastly more material available in the protoplanetary disk. Jupiter is thought to have formed first, starting with a solid core of rock and ice that grew to about 10 times the mass of Earth. Once this core reached a critical threshold, its gravity became powerful enough to initiate a runaway process. It began violently and rapidly pulling in enormous amounts of the surrounding hydrogen and helium gas from the disk. This was not a slow accretion of rocks, but a gravitational avalanche of gas, a cosmic waterfall cascading onto the growing planet. As all this swirling gas from the disk fell inward toward the nascent Jupiter, it conserved its angular momentum, transferring that tremendous rotational energy to the planet. The result was a world that formed by drawing in a huge volume of the disk's fastest spinning material, effectively catching the spin of the entire region. Saturn underwent a similar, though slightly less intense, process, which is why it also spins with such remarkable speed. But this elegant explanation, while powerful, is not the end of the story. It tells us how the giants got their spin, but it doesn't fully explain the specific rates we observe today. This leads to a more subtle and ongoing mystery: what determines the final spin rate of a gas giant? Why does Jupiter spin at precisely 9 hours and 56 minutes and not 10 hours and 10 minutes? This is a far more complex puzzle because a gas giant isn't a solid ball like Earth. Its outer layers are a deep, churning fluid of hydrogen and helium, thousands of kilometers thick, and these layers can rotate at different speeds, a phenomenon known as differential rotation. Jupiter's equatorial zones, for example, rotate about 5 minutes faster than its higher latitudes. This means the planet's day depends on which part of its atmosphere you're measuring. Furthermore, the immense magnetic fields generated deep within these planets interact with the electrically conductive fluid in their interiors, creating a magnetic braking effect that can, over billions of years, very slowly sap rotational energy. The precise final spin we observe today is likely a delicate balance between the initial, furious spin inherited from formation and these subsequent, gradual braking processes that have been subtly slowing them down ever since. It's a fossil record of their violent birth, slightly weathered by the eons, a lasting signature of the whirlwind from which they emerged. Circling the red planet like two frantic celestial moths, the moons of Mars present a puzzle that is deceptively simple in its framing. Where did they come from? Phobos and Deimos are not the grand, spherical companions we see orbiting other worlds. They are small, dark, and lumpy, more akin to overgrown potatoes than proper moons. Their very appearance screams captured asteroid, and for a long time that was the prevailing theory. It seemed to make perfect sense. The asteroid belt lies just next door, and Mars's gravity could have easily snared a couple of passing rocks billions of years ago. Yet, as we've looked closer, this straightforward story has begun to unravel, replaced by a compelling and dramatic alternative that involves a cataclysmic birth for Mars itself. The question of their origin is not just academic. It speaks to the violent history of the inner solar system and the very nature of how planets acquire their companions. The captured asteroid theory is elegant in its simplicity. Mars resides right next to the main asteroid belt, a cosmic shooting gallery full of potential candidates. Phobos and Deimos, with their low density, dark coloration, and irregular shapes, share a striking spectral resemblance to a class of asteroids known as carbonaceous chondrites, which are primitive, water-rich bodies from the outer belt. The idea is that sometime after Mars formed, these two wanderers drifted too close and were gravitationally captured into orbit. This would neatly explain their composition and their atypical appearance compared to a planet-born moon like our own. However, this tidy explanation runs into two massive gravitational roadblocks, their orbits. Both Phobos and Deimos orbit Mars in nearly perfect circular paths that are almost exactly aligned with the planet's equator. This is highly unusual for captured objects. When a planet captures a passing asteroid, the resulting orbit is typically highly elliptical and tilted, a chaotic path that only gradually circularizes over immense spans of time through tidal interactions. The pristine, orderly orbits of Phobos and Deimos suggest they either formed in place from a disk of debris around a young Mars, or they were captured in a way that defies our current models of celestial mechanics. This orbital elegance is the primary fuel for the competing and increasingly favored theory, the giant impact hypothesis. This scenario paints a far more violent and spectacular picture. Imagine the early solar system, a chaotic construction zone. A protoplanet, perhaps 1/3 the size of Mars itself, is on a collision course. It slams into the young red planet with unimaginable force, blasting a colossal plume of vaporized rock and debris high into space, and perhaps even stripping away a significant portion of the early Martian atmosphere. In the aftermath of this cosmic catastrophe, while much of the debris fell back to the surface or escaped entirely, a portion of it settled into a disk of hot material orbiting Mars, much like the disk from which Earth's moon is thought to have formed. From this disk, the smaller, rubble pile moons of Phobos and Deimos coalesced. This theory elegantly explains their circular, equatorial orbits. They formed from a disk that naturally settled into that plane. It could also account for their strange composition if the impactor was a primitive, water-rich body from the outer solar system, mixing its material with the crust of Mars to create the dark, carbonaceous-like material we observe today. Adding a critical ticking clock to this mystery is the fate of Phobos itself. This larger inner moon is in a death spiral. Its orbit is decaying, and it is slowly, inexorably drawing closer to Mars. In several tens of millions of years, it will either be torn apart by Martian gravity, creating a temporary ring around the planet, or it will crash directly onto the surface. This unstable orbit is a key piece of the puzzle. If Phobos were a captured asteroid, its inward migration would be difficult to explain given its current position. However, if it formed from a debris disk, its orbit could have evolved outward from a point closer to Mars and is now, due to complex tidal interactions, beginning its long journey back inward. This dynamic history fits more naturally with an impact origin. Furthermore, the surface of Phobos is crisscrossed with a network of mysterious parallel grooves. For years, their origin was debated, but the prevailing view now is that they are stretch marks fractures caused by the tidal forces of Mars as the Moon is slowly pulled apart. This ongoing destruction provides a unique glimpse into the life cycle of a moon and offers future missions a chance to sample the interior of what may be a reassembled pile of impact debris. The debate is far from settled, and each theory has its own unresolved issues. The impact model must explain why such a colossal collision produced two such small moons and not one large one like our moon. Perhaps the debris disk was too diffuse, or maybe there were originally more moons that have since been lost. The capture theory, meanwhile, must devise a plausible mechanism to circularize and align the orbits so perfectly, a process that remains a significant challenge in dynamical models. The upcoming Martian Moons E-Exploration Mission, or MMX, led by the Japanese space agency JAXA, aims to provide the definitive answer. Scheduled to launch later this decade, MMX will not only orbit Phobos and Deimos but also land on Phobos, collecting samples and returning them to Earth. The composition of those samples will be the ultimate arbiter. If they match the specific isotopic signature of Martian rock, the impact theory will be triumphant. If they reveal a composition alien to Mars and identical to certain asteroids, the capture theory will be vindicated. Moving from the violent, dynamic origins of moons, we arrive at a mystery of a different kind, one not written in rock or ice, but in the seemingly arbitrary spacing of the planets themselves. In the 18th century, as astronomers mapped our solar system with increasing precision, a curious mathematical pattern emerged, a kind of cosmic rhythm hidden in the orbits of the known worlds. This pattern would become known as the Titius-Bode law, an empirical rule that, for a time, seemed to hold the key to the architecture of our solar system, successfully predicting the existence of new planets before they were ever seen through a telescope. It's a story that blends brilliant intuition with eventual disillusionment, a tantalizing clue that continues to spark debate over whether we are seeing a profound truth or a spectacular cosmic coincidence. The law itself is surprisingly simple. Take the sequence 0, 3, 6, 12, 24, 48, and 96, a pattern where each number is double the previous one, starting after the 0. Now add 4 to each number in that sequence. You get 4, 7, 10, 16, 28, 52, and 100. If you then divide each of these results by 10, you get a series of figures that correspond almost uncannily to the average distances of the planets from the Sun, measured in astronomical units. At the time of its proposal, this formula perfectly matched Mercury at 0.40, Venus at 0.7, Earth at 1.0, Mars at 1.6, and Jupiter at 5.2. But there was a conspicuous gap at the position of 2.80 between Mars and Jupiter. This gap was the law's first great prediction. Astronomers, convinced the pattern was real, began a dedicated search for the missing planet in that orbital slot. Their search didn't yield a single large world, but instead led to the discovery of the first and largest asteroid, Ceres, orbiting right where the law said something should be. A short time later, when William Herschel discovered Uranus in 1781, its orbit fit beautifully into the next slot in the sequence, further cementing the law's status as a seemingly fundamental principle of celestial mechanics. For decades, it was considered a major scientific discovery, a Rosetta Stone for decoding the solar system's blueprint. However, the law's reign was not destined to last. The first major crack in its foundation appeared with the discovery of Neptune in 1846. Neptune's actual orbit simply did not fit the neat progression predicted by Titius Bode. It was a glaring misfit, a world that refused to follow the rule that had worked so well for its predecessors. The final blow came with the discovery of Pluto in 1930, which also failed to conform, though by then Pluto's status as a planet was already a matter of debate. The law, which had once seemed so powerful, was ultimately relegated to the status of a historical curiosity, a discredited rule that had, through a combination of luck and selective interpretation, gotten a few things right. The modern consensus views it as a numerical coincidence, a pattern that emerged from the specific conditions of our own solar system's formation, but which holds no universal predictive power. We now understand that planetary orbits are the complex outcome of gravitational interactions, accretion, and migration within the protoplanetary disk, not the product of a simple mathematical formula. Yet the ghost of Titius Bode has never been fully laid to rest. The fact that it predicted the asteroid belt and Uranus with such accuracy continues to nag at scientists. Is it possible that there is a kernel of underlying physics embedded within this seemingly arbitrary rule? Some researchers argue that the pattern we see is a natural consequence of orbital resonances and the way material tends to collect in stable zones within a rotating disk of gas and dust. In this view, the Titius Bode pattern isn't a fundamental law, but rather a statistical tendency, a signature of the dynamical processes that sculpted our particular planetary system. When we look at the regular moon systems of Jupiter and Saturn, we sometimes see similar, though not identical, patterns of orbital spacing, suggesting that such gravitational footprints might be a common, if not universal, outcome. The debate, therefore, is not about reviving the law as a predictive tool, but about understanding what its fleeting success tells us about our solar system's unique history. It stands as a humbling lesson in the history of science, a reminder of our powerful desire to find order in the cosmos, and of the fine line between a pattern that reveals a deep truth and one that is merely a compelling arrangement of numbers, a cosmic mirage that guided us to discovery before fading into the darkness from which it came. But beyond the violent collisions and the grand orbital dances of planets, there exists a phenomenon of breathtaking subtlety, a ghostly light that has haunted the twilight skies for all of human history. This is the zodiacal light, a faint, ethereal pyramid of radiance that can sometimes be seen reaching up from the horizon after sunset or before sunrise, stretching along the path of the ecliptic where the planets travel. Unlike the sharp points of stars, this is a soft, diffuse glow, often described as a false dawn or a lingering twilight. It is sunlight, but sunlight reflected in a way that reveals an entire hidden component of our solar system. This light is scattered by countless trillions of microscopic dust particles that fill the inner solar system, a vast lens-shaped cloud of interplanetary debris through which the Earth and other planets constantly move. Seeing it is like watching sunlight filter through a cosmic haze, illuminating a realm we normally cannot perceive. For centuries, this gentle light was a source of wonder and speculation, but its basic cause, sunlight reflecting off dust, has been understood for a long time. The true and enduring mystery lies not in what the zodiacal light is, but in how it is sustained. These tiny dust grains, constantly buffeted by solar radiation and the solar wind, do not remain in stable orbits forever. They are subject to a relentless process known as the Poynting-Robertson effect, a fascinating consequence of the physics of light itself. As a dust particle orbits the Sun, it absorbs sunlight from directly ahead in its orbit and then re-radiates that energy as heat in all directions. This re-radiation acts like a tiny, gentle brake, constantly sapping the particle's orbital energy. Over time, this causes the particle to spiral slowly but inexorably inward toward the Sun, where it is eventually vaporized. The entire cloud of dust responsible for the zodiacal light would, by all calculations, spiral into the Sun and disappear within a mere 10,000 to 100,000 years, a geological instant compared to the 4.5 billion-year age of our solar system. Therefore, the central puzzle is clear. Something must be constantly and actively replenishing this cosmic dust cloud. A one-time event like the breakup of a single asteroid couldn't possibly account for the persistent glow we observe generation after generation. We are witnessing a dynamic, ongoing process, and the hunt for the primary dust factories is a major astronomical investigation. The prime suspects in this cosmic resupply chain are the solar system's great nomads, comets. As a comet swings in on its elongated orbit from the distant Oort cloud or Kuiper belt, the Sun's intense heat vaporizes its ices, releasing not only gas but also a prodigious amount of trapped dust and grit. This material streams away from the comet's nucleus, forming its magnificent tails. The dust tail, pushed gently by the pressure of sunlight, becomes a river of fresh particles that get smeared along the comet's orbital path. Over thousands of years, as a comet makes repeated passages through the inner solar system, it litters its orbit with a dense trail of debris. When Earth passes through one of these trails, we see a meteor shower. But the collective, steady trickle of dust from all the comets passing through the inner solar system is thought to provide a massive, continuous infusion of new material, constantly topping up the reservoir that creates the zodiacal light. The Jupiter family comets, with their relatively short orbits, are considered especially prolific contributors to this dusty haze. However, comets do not act alone. The second major suspect is the asteroid belt, but not through a single catastrophic event. Instead, astronomers point to a process of perpetual, low-level grinding. The main asteroid belt is not a serene, static collection of rocks. It is a dynamic environment where objects are constantly colliding. While most of these impacts are too small to shatter a large asteroid, they are more than sufficient to chip off surface material, create craters, and generate vast clouds of fine dust through a process called impact grinding. Furthermore, a more exotic mechanism may be at work on the smallest asteroids, the Yarkovsky-O'Keefe-Radzevsky-Paddock or YORP effect. This is a subtle thermal process where the uneven absorption and re-radiation of sunlight can cause a small, irregularly shaped asteroid to slowly change its rotation rate. Over millions of years, the YORP effect can spin some asteroids up so fast that they literally fly apart, centrifugally shedding their outer layers and disintegrating into a cloud of gravel and dust. This steady, grinding destruction across the entire asteroid belt provides a second, relentless source of fine particles that migrates inward to feed the zodiacal cloud. Yet the case is not entirely closed. Observations from space-based telescopes have sometimes revealed more dust in the inner solar system than our current models of cometary and asteroidal dust production can easily explain. This has led scientists to consider other, more surprising contributors. One fascinating possibility involves a population of dark comets, or extremely carbon-rich asteroids that are so dark they are nearly invisible to our surveys, but which could be disintegrating and releasing dust at a higher rate than we anticipate. Another line of inquiry looks even closer to home, examining whether Mars, with its frequent globe-spanning dust storms, could be lofting a tiny fraction of fine material high enough to escape its gravity and join the interplanetary dust complex. While likely a minor contributor, it highlights the complexity of tracking the origins of something as diffuse as a cloud of microscopic particles. The zodiacal light, therefore, is far more than a beautiful celestial curiosity. It is the visible manifestation of the solar system's endless cycle of creation and destruction, a soft glow that speaks to the constant, invisible rain of dust from the crumbling frontiers of our cosmic neighborhood. A testament to the fact that even in the apparent emptiness of space, there is always a gentle, ongoing snowfall. From the gentle glow of interplanetary dust, we now turn our gaze to the very heart of our solar system, to the star that gives us light and life. And here, we encounter a paradox so fundamental it strikes at the core of our understanding of physics. If you were to reach out toward the sun, logic would suggest that the farther you get from its nuclear fusion core, the cooler things should become. This holds true as you move outward from the 15 million degree core, through the radiative zone and into the churning convective zone. At the sun's visible surface, the photosphere, the temperature has dropped to a relatively balmy 5,700 degrees Celsius. This is the light we see, the familiar yellow disk in our sky. But if you continue moving outward into the wispy, pearly white outer atmosphere known as the corona, something extraordinary and utterly counterintuitive happens. Instead of getting colder, the temperature skyrockets. The corona routinely reaches a staggering 1 to 2 million degrees Celsius, and in some regions it can soar to over 10 million degrees. This is the sun's corona heating problem, and for over half a century it has stood as one of the most enduring and baffling mysteries in all of astrophysics. How can the sun's atmosphere be hundreds of times hotter than its surface? It's as if you walked away from a campfire and with each step the air around you became exponentially hotter, a phenomenon that defies every instinct we have about heat and energy. The challenge of observing this superheated envelope has been immense. The corona is incredibly faint, a million times dimmer than the blinding disk of the photosphere, and is normally only visible from Earth during the fleeting, precious moments of a total solar eclipse when the moon perfectly blocks the main body of the sun. It was during these eclipses that early astronomers first glimpsed the corona's ethereal streamers and began to suspect its extreme nature. But to truly study it, we had to go to space. Modern missions like NASA's Solar Dynamics Observatory, the Parker Solar Probe, and the European Space Agency's Solar Orbiter are now diving closer to the sun than ever before, measuring the magnetic fields, particles, and waves in the corona with unprecedented precision. What they've found is a realm of violent, dynamic energy, and the quest to find the engine driving this immense heat has crystallized around two primary competing theories, each with compelling evidence but neither yet offering a complete solution. The first major theory proposes that the corona is heated by a constant, invisible fireworks display of tiny explosions known as nanoflares. We are all familiar with the massive, spectacular eruptions of solar flares, which can unleash energy equivalent to billions of atomic bombs. The nanoflare theory, first proposed by physicist Eugene Parker, suggests that the sun's surface is also seething with an unimaginable number of much smaller magnetic reconnection events. These are mini explosions that release immense energy but are individually far too faint for our telescopes to easily detect. The process begins with the sun's magnetic field, which is generated by the churning plasma in its interior. This field erupts through the photosphere in vast, looping arcs, creating a tangled, chaotic mess in the corona. As these magnetic field lines are stretched and twisted by the sun's rotation and internal motions, they can become stressed to a breaking point. When oppositely directed field lines cross, they can suddenly snap and reconfigure into a new, lower energy state, a violent process known as magnetic reconnection. This reconnection converts immense magnetic energy into heat and kinetic energy, explosively accelerating particles and heating the surrounding plasma. A single nanoflare might be a billionth the power of a large solar flare, but the theory posits that they are occurring everywhere all the time in the countless millions. This relentless, ubiquitous drizzle of miniature explosions could, in aggregate, provide the steady and enormous heat input needed to keep the corona at millions of degrees. It's a compelling idea, like the collective heat from trillions of microscopic matches being struck simultaneously, but directly observing and quantifying these faint, ubiquitous events has proven to be an immense technological challenge. The second leading theory offers a different kind of mechanism, one based not on discrete explosions but on the continuous transport of energy by waves. In this model, the turbulent convection at the Sun's surface, the same boiling motion that creates the granulation pattern we can see, generates powerful waves that travel upward into the atmosphere. Two types of waves are considered prime suspects. The first are Alfvén waves, named after their discoverer, Nobel laureate Hans Alfvén. These are not like sound or light waves. They are ripples that travel along magnetic field lines, much like a wave traveling down a shaken rope. The second type are magnetocaustic waves, a hybrid of magnetic and sound waves. In both cases, the theory suggests these waves are generated with tremendous energy at the photosphere and then race upward along the magnetic loops into the corona. As they travel into the thinner and thinner plasma of the upper atmosphere, their energy becomes more concentrated. Eventually, like an ocean wave crashing onto a shore, they break or dissipate their energy through a process called turbulent cascade, dumping all that pent-up motion directly as heat into the coronal plasma. This would be a more continuous, wave-based heating process, a constant humming vibration that shakes the corona to a fever pitch. There is strong observational evidence for these waves. Spacecraft have detected them coursing through the solar atmosphere. The critical unknown is whether they carry enough energy and dissipate it efficiently enough to account for the corona's immense temperatures, or if they are merely a contributing player in a more complex orchestra of heating mechanisms. The most likely reality, as is often the case in science, is a hybrid one. It is entirely possible that both nanoflares and magnetic waves work in concert to solve the coronal heating problem. Waves might provide a steady, background level of heating, while nanoflares provide more intense, localized bursts of energy. Different regions of the corona, with their varying magnetic field configurations, might be dominated by one mechanism or the other. The quest to unravel this mystery is far from academic. A superheated corona has direct and dramatic consequences for us here on Earth. It is the source of the solar wind, the relentless stream of charged particles that flows outward through the solar system. The dynamics of coronal heating dictate the speed and density of this wind, which in turn shapes the structure of our entire heliosphere and drives the space weather that can disrupt satellites, power grids, and communications on Earth. Understanding how the corona is heated is fundamental to predicting the behavior of our star and safeguarding our increasingly technological society. This puzzle, born from a simple observation of a solar eclipse, has thus blossomed into a grand challenge that pushes the limits of our physics, our technology, and our understanding of the universe, reminding us that even our own star, the most familiar object in the sky, still holds profound and fiery secrets at its brilliant edges. And just when we think we have a handle on the strangest worlds in our solar system, we encounter one that seems to defy logic with a stark, two-faced visage. Journey with us now to the outer reaches of Saturn's domain, to a moon named Iapetus. This is a world of pure cosmic contrast, a celestial yin and yang frozen in space. One hemisphere is as brilliantly white as freshly fallen snow, reflecting vast amounts of sunlight. The other is an incredibly dark, almost charcoal black landscape, one of the darkest surfaces known in our entire solar system. This isn't a subtle gradient, it's a sharp, dramatic line dividing light from absolute darkness, creating a visual paradox that has puzzled astronomers since the moon was first glimpsed centuries ago. The mystery of Iapetus's two-tone coloring is a story of cosmic paintballs, migrating ice, and a world that seems to have turned itself inside out. The leading theory to explain this bizarre appearance is as elegant as it is strange, a process known as thermal migration. The story begins not on Iapetus itself, but with another, more distant moon of Saturn, Phoebe. Phoebe is a dark, irregularly shaped object, and it orbits Saturn in the opposite direction to most of the other moons, a rebellious path known as a retrograde orbit. This backward journey is critically important. As Phoebe is bombarded by micrometeorites, it constantly sheds a fine, dark dust, creating a faint ring of debris that spirals slowly inward toward Saturn. Iapetus, orbiting in the prograde or forward direction, plows directly into this stream of dark material like a car driving into a rainstorm. Because one hemisphere of Iapetus is always facing forward along its orbital path, its leading hemisphere, it acts as a cosmic windshield, collecting a steady rain of this black dust. The trailing hemisphere, meanwhile, remains relatively pristine and clean. This initial dusting sets the stage for a powerful runaway feedback loop. The dark material on the leading hemisphere has a low albedo, meaning it's very good at absorbing sunlight and converting it into heat. As this darkened area warms up, any exposed water ice on the surface sublimates, turning directly from a solid into a gas. This water vapor then travels across the moon and recondenses wherever it is cold enough, which happens to be on the bright trailing hemisphere and at the poles. This condensation makes the bright areas even brighter and more reflective, which in turn keeps them colder. Meanwhile, the now ice-depleted leading hemisphere becomes even darker, absorbing even more heat and driving off yet more ice. Over millions of years, this self-reinforcing process would have amplified a slight initial dusting into the stunning, stark divide we see today. It's a powerful and compelling explanation, painting a picture of a world where a simple coating of dust triggered a planetary scale makeover, effectively sealing one half of the moon in brilliant white and the other in profound black. But Iapetus is a moon that refuses to offer a simple solution. Just when the thermal migration theory seems to neatly wrap up the mystery, we have to contend with another of Iapetus's jaw-dropping features, the equatorial ridge. This is a bizarre, mountainous chain that runs perfectly along the moon's equator, encircling the entire globe like the seam on a giant walnut or a cosmic racetrack. In some places, this ridge soars over 12 miles high, making it one of the tallest mountain ranges in the solar system relative to the size of the body it's on. Its formation is a complete enigma, and its existence is deeply intertwined with the two-toned coloring in ways we don't fully understand. How does a moon grow a 20,000-foot-high wall that precisely follows its equator? Current geological models struggle to explain it. One leading idea is that the ridge is the frozen remnant of a time when Iapetus spun much more rapidly, a relic of a ring system that once surrounded the moon and then collapsed down onto its surface. Another theory suggests it could be the result of a colossal upwelling of material from the moon's interior that somehow extruded only at the equator. Crucially, this ridge plays a direct role in the color mystery. The dark material, known as the Cassini Reggio, doesn't simply stop at the ridge. In many areas, it appears to flow over it, suggesting the ridge was present before or during the darkening process. The complex topography created by the ridge would have influenced how the dark dust settled and how the water ice migrated, creating intricate patterns and boundaries between the light and dark regions that are far more complex than a simple leading trailing hemisphere divide. This combination of the two-tone coloring and the equatorial ridge makes Iapetus a unique geological puzzle box. The ridge itself may even hold clues to the very initial conditions that allowed the thermal migration process to begin. Some scientists speculate that the ridge's formation could have altered Iapetus's global heat flow or created shadowed regions that acted as cold traps, preferentially capturing the initial infall of dark dust and kick-starting the entire feedback loop. The problem is that we have only had a few close, detailed looks at this strange world, primarily from the Cassini spacecraft's flybys. While Cassini provided us with breathtaking images and data, a single visit often raises more questions than it answers. To truly unravel the intertwined secrets of Iapetus's paint job and its massive seam, we would need a dedicated orbiter, a mission that could map its surface in extreme detail, analyze the precise composition of both the dark and light materials, and probe its internal structure to understand the forces that built the ridge. Until then, Iapetus remains a stark, beautiful, and silent testament to the fact that even within a single moon, multiple grand mysteries can coexist, each one making the other more profound and more compelling. It is a world of two stories, one written in migrating ice and alien dust, the other in a mountain range that defies explanation, forever locked in a gravitational embrace around its ringed parent. Yet, for all the strange signals and swirling storms we've encountered, perhaps the most humbling mystery is one we can never actually hear, a deep, pervasive static that underlies the entire cosmos, a sound so loud it drowns out the whispers of the universe's infancy. This is the phenomenon known as the space roar, and its discovery was a complete accident, a case of scientists turning up the volume on the cosmos only to find it was screaming at a pitch they never expected. The story begins not with a search for the inexplicable, but with a carefully designed NASA mission named Arcade, which stands for the absolute radiometer for cosmology, astrophysics, and diffuse emission. Launched in 2006 aboard a high-altitude balloon, Arcade's primary goal was to peer back in time, attempting to detect the faint, predicted radio static from the very first stars that ignited after the Big Bang. These primordial giants, thought to be hundreds of times more massive than our Sun, would have flooded the early universe with radio waves as they lived their short, violent lives. To find this whisper from the dawn of time, Arcade was exquisitely sensitive, calibrated to measure the faintest possible signals in the radio portion of the electromagnetic spectrum. But when the scientists analyzed the data, they were met with something that defied all their models and expectations. The sky wasn't faintly whispering, it was roaring. Arcade had detected a radio signal that was 6 times louder than anyone had predicted. A booming, pervasive hiss that had no clear origin. It wasn't coming from any one point in the sky. It was everywhere, a uniform blanket of unexplained noise that permeated the entire celestial sphere. This was not the subtle signature of the first stars. This was something else entirely, a background cacophony so intense that it completely obscured the very signal they were trying to find. The immediate challenge for astronomers was to account for every possible known source of radio emission and subtract it from this deafening signal. They meticulously catalogued and removed the collective radio murmur from all the known galaxies in the universe. They accounted for the faint emission from the outer halo of our own Milky Way. They even subtracted the contribution from every known radio source that had ever been identified. Yet, when all of that was stripped away, the roar remained immense, persistent, and utterly mysterious. This left scientists with 2 profoundly different categories of explanation, each with staggering implications. The first possibility is that the roar is cosmological in origin, meaning it is a fundamental part of the universe's structure. If this is true, it would force a complete rewrite of our theories of cosmic evolution. What process in the early universe could have generated such an intense, uniform radio background? Could it be the collective signal from a previously undetected population of ultra-faint, star-forming galaxies, so numerous and so distant that their individual radio whispers blend into a single, overwhelming roar? Or does it point to a more exotic physical process, perhaps related to the decay of theoretical particles from the dark matter that permeates the cosmos? A cosmological origin would mean we are fundamentally misunderstanding the radio sky and the total energy budget of the universe. The other major possibility is that the roar is not cosmological at all. but is instead a foreground, a veil of radio emission originating from within our own local cosmic neighborhood that we have not yet learned to see through. The prime suspect in this scenario is a vast, unseen population of faint, isolated radio sources within our own galaxy. Imagine a celestial fog made not of water vapor, but of countless dim stellar corpses. Rogue planets unmoored from any star with powerful auroras crackling in their magnetic fields, or solitary brown dwarfs, failed stars too cold to shine in visible light but potentially brilliant in radio waves. There could be vast, diffuse clouds of electrons swirling in the magnetic fields of interstellar space, emitting a steady, faint radio hum that our current surveys are simply not sensitive enough to resolve into individual points. If the roar comes from this unseen foreground, the mystery shifts from cosmology to galactic astronomy. It becomes a challenge of inventory, a call to create a more complete census of the faint, radio-emitting objects that drift unseen in the dark spaces between the stars. The enigma of the space roar persists because it sits in a frustrating observational gap. Our radio telescopes are incredibly powerful, but they are often designed to study specific, point-like sources like quasars or pulsars. They can struggle to accurately measure a perfectly smooth, uniform background signal that covers the entire sky. New instruments and sky surveys are now being developed with the specific goal of mapping the radio sky with unprecedented sensitivity, hoping to either resolve this roar into a trillion faint, individual points or confirm that it is truly a fundamental feature of the cosmos. Until then, the space roar stands as a monument to our ignorance, a reminder that even when we listen to the universe with our most advanced technology, we can still be surprised by a voice we did not anticipate, a deep, pervasive static that asks more questions than it answers about the true nature of the space between the stars. But to truly grasp the dynamic nature of our solar system, we must abandon the idea that it has always looked the way it does today. We have to travel back to its chaotic infancy, a time when the giant planets were not the stable, distant sentinels we know, but restless giants on the move. There is now compelling evidence that Jupiter, Saturn, Uranus, and Neptune underwent a grand and violent migration, completely reshaping the architecture of our cosmic neighborhood in their wake. This isn't just a theoretical exercise. It's a detective story written in the orbits of asteroids and the craters on the Moon, and it provides the most elegant solutions to some of the very mysteries we've already explored. The first major clue that something was amiss came from a detailed study of the asteroid belt. For a long time, this region between Mars and Jupiter was considered a failed planet, a place where material never quite managed to coalesce. But the Grand Tack model, named after the sailing maneuver, proposes a far more dramatic history for Jupiter. In this scenario, the young Jupiter, having formed first, began to drift inward toward the Sun, its immense gravity carving a gap in the protoplanetary disk. It may have journeyed as far inward as the orbit of Mars is today, acting as a gravitational wrecking ball that scattered the building blocks of potential planets and preventing the formation of a larger world in that region. This inward migration explains why the inner solar system is so relatively small and compact. But then Saturn entered the picture. As Saturn formed and began its own inward migration, it eventually caught up to Jupiter, and the two planets became locked in a gravitational dance known as an orbital resonance. This resonance, like two cosmic cogs locking together, reversed their direction. The combined gravitational pull of the two giants sent them both drifting back outward to their current positions. This tack by Jupiter sailing inward and then outward explains the strange composition and sparse nature of the asteroid belt. It swept the region clean of most material, leaving behind only a small fraction of the original debris, a fossilized record of the giant planet's epic journey. This initial reshuffling was just the prelude to an even more dramatic event, detailed in the later NICE model. After the grand tack, the four giant planets were in a much more compact, closely packed configuration, nestled within a vast, dense disk of icy planetesimals beyond the orbit of the youngest Neptune. For millions of years, these planets gently gravitationally nudged the countless small icy bodies in this disk. But physics is a two-way street. Every time a planetesimal was flung inward by a planet's gravity, the planet itself received a tiny recoil, pushing it slightly outward. This slow, steady exchange of momentum caused the planets to migrate. The pivotal moment came when Jupiter and Saturn once again entered a powerful orbital resonance, this time with Saturn completing exactly 2 orbits for every one of Jupiter's. This 2-to-1 resonance sent a powerful gravitational shockwave through the entire system. The previously smooth migration process broke down into chaos. The orbits of Uranus and Neptune became violently unstable. They were flung outward, plowing through the pristine disk of icy bodies like cosmic bulldozers. In some versions of the model, Neptune and Uranus may have even swapped places. This event scattered the primordial disk, flinging a vast swarm of these icy objects inward toward the Sun. This incoming hail of comets and asteroids is what we now call the Late Heavy Bombardment, that period of intense planetary pummeling that scarred the Moon and the inner planets around 4 billion years ago. The migration of the giants, therefore, provides the long-sought trigger for that ancient cataclysm, linking the violence in the inner solar system directly to the gravitational turmoil in the outer realms. The consequences of this great migration extend all the way to the solar system's frozen frontier, the Kuiper belt. Before the planetary reshuffling, this belt was likely far more massive and extended much closer to the Sun. As Neptune migrated outward, its gravity shepherded and sculpted the remaining icy debris. It pushed a vast population of objects into the stable, resonant orbits we see today, where they orbit in sync with Neptune. But it also explains the Kuiper belt cliff, that sudden drop in objects beyond 50 astronomical units. Neptune's migration essentially swept that region clean, either flinging the objects inward or ejecting them from the solar system entirely, leaving behind the stark boundary we observe. This model also provides a plausible origin for the detached, high-inclination objects like Sedna, whose strange, elongated orbits suggest they were violently flung outward during this period of instability and have been drifting in the deep freeze ever since. The entire structure of our outer solar system, from the resonant Kuiper belt objects to its sharp outer edge, appears to be a direct fossil of this ancient planetary dance. The migration of the giant planets is no longer just a compelling theory. It is the foundational narrative that ties together the history of the inner and outer solar system, explaining with a single, grand sequence of events the very clues that once seemed like disconnected mysteries. And yet, for all the evidence of this ancient planetary migration, the gravitational story of our outer solar system may not be a finished book. The very same clues that pointed to that past reshuffling, the strange orbits of distant objects, are now whispering of a possible current resident, a hidden giant whose influence is felt but never seen. This brings us to one of the most thrilling and contentious modern astronomical quests, the hunt for Planet 9. The story begins not with a glimpse in a telescope, but with a pattern discovered in the data. Astronomers studying the distant Kuiper belt began to notice that the most far-flung objects, those with orbits taking them hundreds of astronomical units from the Sun, were not randomly oriented. Instead, their elongated paths appeared to be clustered together, as if an invisible hand were shepherding them, keeping their points of closest approach to the Sun, their perihelia, bundled up in one region of the sky while their orbits were all tilted in a similar direction. This is astronomically bizarre. The relentless gravitational tug from the known giant planets should have randomized these orbits over billions of years, scattering them like leaves in the wind. The persistent clustering is a huge red flag, a statistical anomaly so significant that it strongly suggests the presence of a persistent external gravitational force. The most elegant and dramatic explanation is that a massive yet undiscovered planet is orchestrating this cosmic ballet from the shadows. So, what kind of world could this be? Based on the strength of its gravitational influence, the hypothetical planet 9 is no puny dwarf planet. Estimates suggest it could be a super-Earth or a mini-Neptune, with a mass roughly 5 to 10 times that of our own world. Its orbit, however, is where it truly becomes a creature of the deep dark. It's thought to be tremendously elongated and tilted, a lazy, sprawling ellipse that takes it from a perihelion of perhaps 250 astronomical units out to an incredible aphelion of 600, 800, or even over 1,000 O. A single orbit for this proposed planet could take between 10 and 20,000 Earth years to complete. It would be a frozen, dimly lit world, so far from the sun that our star would appear as little more than an exceptionally bright point of light lost in a sea of others. This proposed orbit also explains why we haven't found it yet. Our major sky surveys have primarily focused on the plane of the solar system, while Planet 9, according to the models, could be spending most of its time far above or below that plane, hiding in the vast, under-surveyed expanse of the celestial sphere. The search for this phantom planet is a monumental challenge, a high-stakes game of celestial hide-and-seek played across the entire sky. Astronomers are using some of the world's most powerful telescopes, like the Subaru telescope in Hawaii, to conduct a painstaking pixel-by-pixel scan of the most likely regions of space. They're not looking for a bright, obvious disk, but for a faint, star-like point that moves ever so slightly against the background of fixed stars over nights, weeks, or months. The Vera C. Rubin Observatory, scheduled to begin its operations in the next few years, will be a game-changer in this hunt. With its enormous mirror and massive digital camera, it will repeatedly image the entire visible sky, automatically flagging any object that moves. If Planet 9 is where the models predict Vera C, Rubin has an excellent chance of finding it, finally turning a gravitational ghost into a real, observable world. Of course, such a radical hypothesis naturally invites skepticism and alternative explanations. Some scientists have proposed that the gravitational anomalies could be explained not by a single large planet, but by the collective pull of a swarm of smaller, undiscovered Kuiper belt objects whose combined mass creates a similar shepherding effect. Others have looked to more exotic possibilities, such as the gravitational influence of a primordial black hole, a leftover from the Big Bang with the mass of a planet but compressed into an object no larger than a grapefruit. This black hole alternative, while far less likely, is a testament to how puzzling the orbital evidence truly is. However, the Planet 9 hypothesis remains the most comprehensive and physically plausible solution, as it also neatly explains other solar system oddities, like the existence of objects with orbits perpendicular to the planetary plane and the mysterious tilt of the Sun's axis. The ongoing search is therefore about much more than just adding a new planet to our textbooks. It is a fundamental test of our understanding of gravity on the largest scales within our own system. Finding Planet 9 would be a monumental discovery, revealing a major new chapter in our solar system story. But failing to find it, despite an exhaustive search, would be equally profound, forcing us to completely rethink the forces that have sculpted the outermost reaches of our cosmic home. But even an ancient Titan is not immune to the passage of time, and our return to Jupiter's great red spot reveals a world in the midst of a profound metamorphosis. For centuries, this storm was a fixture of such immense scale that you could fit 3 Earths side by side within its swirling crimson borders. Yet, the continuous observations from telescopes and spacecraft over the past several decades have documented a clear and accelerating trend. The Great Red Spot is shrinking. From its historically documented size, it has diminished to a point where now only a single Earth could comfortably fit within its vortex. Concurrently, its shape has been evolving, transforming from a distinct oval into a more circular form. This isn't a temporary fluctuation. It's a sustained transformation that forces us to ask a deeply compelling question about the ultimate fate of this legendary storm. Will it continue to wither away until it vanishes entirely from Jupiter's cloud tops, or will it find a new, smaller equilibrium, a permanent but diminished version of its former self? Understanding the forces behind this shrinkage is key to predicting its future, and it plunges us directly into the complex and alien fluid dynamics of a gas giant's atmosphere. The Great Red Spot is not a simple hurricane. It's a high-pressure anticyclone, a massive swirling pancake of gas that acts as a barrier between two of Jupiter's most powerful opposing jet streams. Think of it as a colossal atmospheric wheel spinning counterclockwise, trapped between two raging rivers of wind moving in opposite directions. Its energy comes not from warm ocean water like terrestrial hurricanes, but from the smaller eddies and storms that it constantly consumes and from the immense internal heat welling up from Jupiter's core. The shrinking suggests that the delicate balance of forces that has sustained the spot for so long is being disrupted. One leading theory points to changes in these very jet streams. If the velocity or the shear between these adjacent atmospheric rivers is altering, perhaps due to internal planetary processes we cannot yet observe, it could be effectively starving the vortex, reducing its ability to draw in energy and smaller storms, causing it to slowly dissipate. Another possibility involves interactions with other large storm systems on Jupiter. We have observed other, smaller anticyclones occasionally getting drawn into the spot's periphery, and these chaotic mergers could be robbing it of its structural integrity or altering its spin. The changing color of the storm adds another layer of intrigue to this puzzle. The spot's iconic red hue has been known to deepen and fade in cycles that don't always neatly correlate with its changes in size or shape. The exact chemistry that produces this rust-like color remains one of planetary science's great debates. The most prevalent theories suggest that the violent churning of the storm acts as an elevator, dredging up material from deeper within Jupiter's atmosphere. As these chemicals are upwelled into the higher altitudes, they are exposed to intense ultraviolet radiation from the sun, which could be breaking down simpler compounds like ammonia and acetylene into more complex hydrocarbons that have a reddish tint. Alternatively, the coloring agent could be phosphorus or sulfur compounds. If the storm is shrinking and its internal dynamics are changing, the rate and depth at which it pulls up these deeper atmospheric layers could be fundamentally altered, explaining the fluctuations in its color. The spot's appearance is a direct visual readout of its internal chemical and physical state, a changing portrait we are still learning to interpret. What then does the future hold for this giant? The range of possibilities is stark. If the current trend continues unabated, we could be witnessing the final act of a storm that has raged for centuries. It may continue to shrink and weaken until its rotational energy is no longer sufficient to maintain its coherence, at which point it would simply unravel and dissipate, becoming just another patch of turbulent clouds in Jupiter's tempestuous atmosphere. This would be a poignant end to a celestial landmark. However, many scientists suspect a different outcome. The storm might not vanish completely. Instead, it could be approaching a new, stable size. As it contracts, its spin rate may increase due to the conservation of angular momentum, the same principle that causes a figure skater to spin faster when they pull their arms in. This increased rotational velocity could create a more robust and compact vortex that is better able to resist the shearing forces trying to tear it apart. It may find a new, smaller equilibrium where the energy it gains from its environment perfectly balances the energy it loses, allowing it to persist indefinitely as a smaller but still formidable feature. The ongoing transformation of the Great Red Spot is far more than just the slow death of a storm. It is a live, planetary-scale laboratory. By watching it change, we are gaining unprecedented insight into the life cycles of weather systems on gas giants, both in our own solar system and on the countless exoplanets we are discovering around other stars. It teaches us that even the most stable-looking features in the cosmos are dynamic and evolving. The data we gather from its final act, whether that act lasts for decades or centuries more, will be crucial for refining our most sophisticated climate models of Jupiter. It forces us to look deeper, to question what internal mysteries of heat flow, chemistry, and fluid dynamics we have yet to uncover. The great red spot's enduring lesson is that nothing in the universe is truly permanent, and that by witnessing its change, we are learning the fundamental rules that govern the atmospheres of worlds across the galaxy. And so we come to our final destination on this tour of cosmic mysteries, a place that proves you don't need to travel to other worlds to find enigmas that defy easy explanation. We are ending our countdown not in the depths of the outer solar system, but right here in the protective embrace of our own planet's magnetic field, or more accurately, in a place where that embrace falters. High above the Atlantic Ocean, off the coast of Brazil, lies a vast and peculiar region that astronauts and satellite operators have come to view with a mixture of respect and apprehension. This is the South Atlantic Anomaly, often dubbed the Bermuda Triangle of space, and it represents a profound weak spot in the Earth's magnetic shield, a dip in our planetary defenses that has very real consequences for the technology we send into orbit and the humans who venture there. To understand this anomaly, we first need to grasp the nature of the shield itself. Our planet is enveloped in a magnetic field, generated by the churning motion of molten iron in its outer core. This field extends far out into space, creating a protective bubble called the magnetosphere. This bubble deflects the constant, lethal stream of charged particles hurled our way by the sun, the solar wind. It also traps some of these particles in two donut-shaped zones of intense radiation known as the Van Allen belts. Think of these belts as a kind of high-energy prison, where protons and electrons are captured and spiral endlessly along the Earth's magnetic field lines. Normally, these belts are held at a safe distance, thousands of kilometers above our heads, but in the region of the South Atlantic Anomaly, something strange happens. Because the Earth's magnetic field is significantly weaker here, as if someone has pressed a thumb into the invisible field, the inner Van Allen belt dips much closer to the planet's surface, coming within 200 kilometers of altitude, right into the realm where the International Space Station and countless satellites operate. This dent in our magnetic field turns a routine orbital passage into a hazardous event. When a spacecraft like the Hubble Space Telescope or the ISS flies through the anomaly, it is no longer fully shielded from the intense radiation of the inner Van Allen belt. It's like flying from safe, calm air directly into a storm of high-energy particles. For sensitive electronics, this passage is a moment of vulnerability. These particles can punch through shielding, causing temporary glitches, corrupting computer memory, and even triggering permanent damage to solar panels and scientific instruments. To cope, satellite operators often put their most sensitive systems into a protective safe mode as they pass overhead. For astronauts on the space station, the effect is even more personal. They report seeing strange flashes of light behind their closed eyelids, a phenomenon called cosmic ray visual phenomena, caused by high-energy particles directly stimulating their retinas. While the station's hull provides substantial protection, the increased radiation dose during these minutes-long passages is carefully monitored, as prolonged exposure is a significant health risk for long-duration spaceflight. This region is not just a curiosity, it is a persistent and operational challenge for our entire space-based infrastructure. The million-dollar question, of course, is why. What causes this specific and dramatic weakening of our planet's magnetic field? The answer appears to lie not on the surface, but thousands of kilometers below our feet in the turbulent, liquid iron outer core. The prevailing theory points to a colossal reservoir of dense rock sitting at the boundary between the Earth's core and its mantle, deep beneath the African continent. This structure, known as the African Large Low Shear Velocity Province, is essentially a massive continent of rock buried within the planet. It is denser and hotter than the surrounding mantle, and scientists believe it acts as a kind of thermal blanket, disrupting the normal flow of heat from the core, and in the process interfering with the colossal convective currents that generate our magnetic field. It's as if a giant, invisible obstacle is disrupting the smooth flow of the geodynamo beneath the South Atlantic, resulting in a magnetic field that is significantly weaker and more complex over this vast area. But the mystery doesn't end with its cause. It deepens with its behavior because the South Atlantic anomaly is not a static feature. It is evolving, and in ways that have scientists watching with keen interest. Over the past several decades, careful measurements have shown that the anomaly is not only getting progressively weaker, but it is also slowly splitting in two. Data from the European Space Agency's Swarm satellite constellation has revealed the emergence of a second, separate center of minimum magnetic strength developing over the Indian Ocean, suggesting the single, vast weak spot is dividing into a pair. This evolution is part of the broader and perfectly normal process of our planet's magnetic poles wandering and occasionally flipping entirely, a process that has happened countless times in Earth's history. The current changes suggest that the flow of molten material in the core is undergoing a significant reorganization. While this doesn't signal an imminent pole reversal, it does provide a living laboratory for studying one of the most fundamental and dynamic processes of our planet. We are witnessing in real time the deep, hidden machinery of Earth restructuring its own protective shield, with the South Atlantic anomaly serving as the most visible and consequential symptom of that grand planetary scale transformation. This magnetic soft spot forces us to completely rethink the logistics and engineering of our future in space. As we plan for a new era of space stations, lunar gateways, and crewed missions to Mars, the South Atlantic anomaly presents a persistent and growing operational headache. Every satellite in low Earth orbit, from communication constellations to Earth observation platforms, must be hardened against the increased radiation it encounters during its multiple daily passes through this region. This isn't a minor consideration. It drives up the cost, weight, and complexity of every single spacecraft we launch. For the dream of a bustling economy in Earth orbit, with thousands of satellites providing global internet and monitoring our planet's health, the anomaly is a fundamental environmental constraint, a recurring storm of particles that every vehicle must be designed to weather. And for human spaceflight, the stakes are even higher. As we design the next generation of space stations and plan for longer duration missions, shielding astronauts from this concentrated radiation dose is a primary concern. Future habitats might require dedicated storm shelters, areas with extra thick walls where crews can retreat during their 10 to 15-minute passage through the anomaly, a necessary precaution to protect them from the increased risk of cancer and other radiation-induced health effects. This isn't a distant problem. It's a present-day design challenge that will shape the blueprints of every crewed spacecraft for decades to come. To manage this risk, scientists are engaged in a continuous, global effort to monitor the anomaly's behavior with exquisite precision. This isn't a task for a single satellite. It requires a fleet. Missions like the European Space Agency's Swarm constellation, a trio of identical satellites, are dedicated to mapping the Earth's magnetic field in finer detail than ever before. They act like medical scanners for the planet, tracing the subtle shifts and fluctuations in the magnetosphere. What they've recorded is a clear and accelerating trend. The anomaly is not only getting weaker, but it's also spreading westward and slowly splitting into two distinct lobes, one over South America and the other emerging over the Indian Ocean. This data is fed into sophisticated computer models that attempt to forecast the anomaly's future evolution. By understanding how it's changing, satellite operators can adjust the orbits of their spacecraft to minimize exposure, and engineers can develop new, more resilient materials and electronics. This constant vigilance transforms the anomaly from an unpredictable hazard into a known quantity, a mapped danger zone that we can navigate with increasing confidence, even as the zone itself continues to shift and grow. These observed changes inevitably lead to one of the most profound questions in geophysics. Is the South Atlantic anomaly a precursor to a full-scale reversal of Earth's magnetic poles? We know from studying the magnetic fingerprints locked in ancient volcanic rocks that our planet's magnetic north and south poles have swapped places hundreds of times in its history, with the last major reversal occurring about 780,000 years ago. These flips aren't instantaneous. They are messy, drawn-out processes that can take thousands of years to complete. During a reversal, the magnetic field doesn't vanish, but it becomes far more complex and much weaker overall, potentially developing multiple anomalies like the South Atlantic one all across the globe. The dramatic weakening and splitting we see today bear a striking resemblance to what computer simulations suggest the early stages of a reversal might look like. However, it's crucial to maintain perspective. While the anomaly is a significant feature, the Earth's magnetic field as a whole is still orders of magnitude stronger than it would be during a full-blown reversal. Scientists are deeply divided on whether we are truly witnessing the beginnings of a flip or simply a large but temporary fluctuation in the field's strength. The evidence is not yet conclusive, making this one of the most active and watched debates in the field of geomagnetism. Ultimately, the greatest significance of the South Atlantic anomaly may not be the practical problems it creates, but the unique window it provides into the hidden workings of our planet. We cannot journey to the Earth's core, but the magnetic field is a direct projection of the furious, chaotic motions occurring 3,000 kilometers beneath our feet. The anomaly is like a fuzzy television signal caused by interference from a specific source deep within the planet. That source is widely believed to be a colossal, dense structure sitting at the boundary between the molten outer core and the solid mantle, a region known as the African Large Low Shear Velocity Province. Think of this as a massive underground mountain range, but one made of material denser than the surrounding rock. This structure acts as a kind of roadblock, disrupting the smooth, convective flow of liquid iron that generates our magnetic field. It's as if a giant is stirring a pot of molten metal, but a huge rock is sitting at the bottom, creating a persistent swirl and a weak spot in the churning motion directly above it. By studying the precise shape and evolution of the South Atlantic anomaly, we are indirectly mapping the contours of this deep Earth structure, learning about the composition and dynamics of a realm that is otherwise utterly inaccessible to us. This weak spot in our sky, therefore, is a powerful reminder that our planet is a dynamic, living system. Its beating heart of liquid iron drives a protective magnetic shield that is constantly in flux, and the South Atlantic anomaly is the most visible sign of that perpetual planetary transformation. And so, here we are at the end of our grand tour, having journeyed from the scorching vortex of Venus to the icy cliff at the edge of the Kuiper belt. We've witnessed a hexagon spinning at Saturn's pole, listened for a ghostly signal from the stars, and felt the unsettling dip in our own planet's magnetic shield. These 25 unexplained phenomena present a breathtaking tapestry of cosmic questions. They span the entire spectrum from the planetary, the shrinking eye of Jupiter's great red spot and the methane whispers from Mars, to the lunar, like the two-toned face of Iapetus and the violent origins of Phobos and Deimos. We've ventured into the gravitational, chasing the phantom of Planet 9 and unraveling the ancient migration of the giant worlds, and we've even peered into the very heart of our sun, baffled by its mysteriously superheated atmosphere. This incredible diversity is a powerful reminder that the universe's creativity in posing riddles is limitless. It is crucial to understand that these puzzles are not signs of science failing, they are the exact opposite. They are the vibrant, beating heart of the scientific process, Every anomaly, every contradiction, every observation that doesn't fit our current models is not a wall but a doorway. The pioneer anomaly forced us to become better engineers. The faint young sun paradox compels us to rethink the delicate balance of a habitable world. The WOW signal drives us to build more sensitive telescopes and to listen more intently to the cosmic silence. These mysteries are the engines of discovery, the very forces that push us to question, to experiment, and to refine our understanding of reality. They are invitations to explore, and with each new mission, each more powerful telescope, we gather another piece of the grand puzzle. So, as you step away from this journey and look up at the night sky, let it be with fresh eyes. See it not as a static picture in a textbook, but as a living, breathing, and deeply mysterious realm. That bright point of Venus holds a swirling, double-eyed storm. The faint, glowing band of the Milky Way is backlit by a deafening, unexplained radio roar. The quiet certainty of the moon's face hides a violent, lopsided history. The cosmos is not a place of settled answers, but a frontier of magnificent questions, and we are all citizens of this frontier. We want to hear which of these enigmas captured your imagination the most. Did the fleeting brilliance of the WOW signal send a shiver down your spine? Does the relentless decay of Phobos fill you with a sense of cosmic drama? Or does the sheer geometric perfection of Saturn's hexagon leave you in awe? Share your thoughts in the comments below. Let's continue this conversation and celebrate the wonder of not knowing together. The greatest discovery is that there is always more to discover.